abstracts that were submitted that we have Antarctica that are presenting today. So I think that's pretty cool. Antarctica that are presenting today. So I think that's pretty cool. Kind of points to the just how big an effort this is. And
CIG and the convection heat, but we simplify into one variable, the Q traffic in the model. Similar to the building energy flux, here we add the traffic heat into the canyon floor. So the building surface balance equation has a new variable here. Then the isopogenic heat flux is calculated as the sum of building heat space heating flux, the waste heat flux, and the traffic-related heat flux. To estimate the traffic heat, we used a bottom-up approach. The bottom-up means we use the traffic data like traffic volume and the length of road length. It's different from a top-down approach using energy inventories for country or larger regions. Here we have two morphological parameters. They are constant and derived based on the surface input. Like the CTSM's default surface input already has the width of impervious road, which is used to calculate the number of vehicle lanes. And we also can calculate the road width So we provide the time varying variables. Here is annual varying heat release per vehicle. We classified the vehicle into four types, including the gasoline vehicle, diesel, hybrid electric vehicle, and electric vehicle. These four have different fuel economy. And we also have annually varying and hourly varying vehicle flow. It comes from the annual average daily traffic volume and multiplied with a factor to represent the volume at the hour of the day. Thirdly, we consider the weather condition as the climate model provides the rainy and snowy conditions. These variables can be used to quantify the vehicle speed in the rainy and rainy days. The model modification is that the CTSM already have urban traffic this name list, but is disabled now, so the traffic heat is zero. We continue to use it and provide a new module. So the urban vehicle type, this module will read in the vehicle flow for urban land units, the top building district, high density and medium density, as well as the fraction of four vehicle types at the model initialization stage. And the urban parameter type, this module will initialize the constants from the surface data that provide the two morphological parameters to calculate the traffic heat in this urban flux module. Then the urban flux is used by the energy flux type, this module, for further computation. The model validation is conducted at two sites. One is the capital of Toulouse, France. We find this site is densely built and it has morning traffic rush. The annual average daily traffic volume is 4,400 vehicles per lane in a day. It has 40% of gasoline vehicles and 60% of diesels. So the calculated annual mean traffic heat is around 22 watt per meter square. Another site is at Manchester. It's sparsely built and it has afternoon traffic rush. The annual average daily traffic volume is similar to the France one. It's 4,700 vehicles per lane in a day. It has more gasoline vehicles, less diesel vehicles, and a small fraction of hybrid electric vehicles in 2022. So the calculated annual mean traffic heat flux is around 16 watt per meter square. We conduct a pair of simulations. The control one uses the default model configuration. So it only has isotropogenic heat flux from the building energy model. We also have TRAF, this simulation, additionally calculate the traffic heat. So these two plots show the sensible heat flux. The vertical axis on the left is the magnitude, and the right side is the difference in sensible heat flux between the traffic simulations minus the control one. We find that calculate the traffic heat can narrow the underestimation of sensible heat flux at the front site, particularly in summer and during the day. At the UK side, we also find the temperature and the relative humidity is improved. That in winter we find a higher temperature increase due to the traffic heat. So for if it will result in better isopropyl heat flux, hard to say that because isopropyl heat flux is difficult to calculate it, and the established data set like the 1 kilometer data set AH4 GUC, it has three sectors, and the magnitude, the values is 40 at the France side and 12 at the UK side. But if we only account for the building heat related AHF, it's likely to underestimate the AHF. So incorporate the traffic one might have closer AHF to existing data sets. Another thing is the temperature increase. This plot showed the delta temperature, so the difference in TRAF simulation and the control simulation to show the temperature increase in ground, in canopy air, and in building indoor. So we find that the France one has a higher temperature increase than the UK one, so their annual average daily traffic volume are similar. That is partially because of the morphological factors, like the France one has a narrow canyon and less pervious road and more building, so the traffic heat is absorbed within the canyon. Besides the morphological parameters, here we summarized the different factors might influence the traffic-induced urban warming effects, like the vehicle types and the traffic rush hour. An evening traffic rush is more likely to induce nighttime warming, and the background climate is also play a role as both sites, UK one and France one, is at the temperate climate zone, so they are sensitive to traffic heat. In the future, we may run more single-point simulations to validate the module and containerize the model. The next presenter, Junjie, will show the Docker may be more convenient for those single-point simulation. And we are also collecting the global traffic data and prepare for the global simulations. Might we can provide simulated isopropyl heat flux and comparison to existing data sets. So thanks. Any questions or comments?
Great. Any questions for Juan? I had one question, and this is maybe just my own naivety about the urban model. So these are all single point urban plumber sites that you're running?
The France one is from the urban plumber, so it provides the flux variables, and the UK one is using the sensor data, local sensor data. Is not a urban plumber site.
Okay. And then how are you characterizing the land surface for the urban model? You said that the cities basically differed in their kind of I can't remember what you had, but there are physical characteristics of the cities that were different. And I'm just curious if for these, like for the urban plumber sites, if we're able to provide surface data that kind of represents the different cities that are represented in those sites?
Uh, you mean that maybe I can use more urban plumber sites?
No, I guess I'm just kind of curious, and maybe this is a question for Keith too, like what we're doing for surface, like how we're modifying, or if we're modifying surface data sets for the tower sites. I'm used to thinking about this in ecosystems, but not for urban ecosystems.
Mm. Another thing is we do not find suitable traffic data for those urban plumber sites.
Okay, great. Yeah, Charlie.
Okay,
Also,
thank you.
totally random question. It's something I've just wondered about in life. Is there any significant latent heat flux from traffic exhaust too, or is it only the central heat flux that matters?
Uh, Sorry, I do not understand your
Is the
question.
latent heat flux from, from just water vapor in traffic exhaust, is that a relevant term to the energy budget, or is it just the sensible heat flux that matters?
Yeah, here we assume the 1% of sensible heat flux, but previous urban models like TEB model, it constitute like 2% or 5% for the moisture flux.
Great. I see that you're there. And can you share your screen?
Yes.
And Jinji's going to talk about containerized model for CESM.
Yeah. Hi. Can you
Yes,
hear me
yes.
and see my screens?
Yep, we do.
Okay. Thank you very much. It's a very nice chance to share my PhD project, one of my PhD projects about the integration and executions of community land model urban in a container environment. So this project is likely to expand the use of the community land model urban to lots of the communities in the scientific and also local authorities and some other other people just interested in running the urban climate model or knowing something about the urban climates. So so here I want to make some details about how the urbanization will change the local climates. And as we know, the urbanization can build up some build these structures in the urban areas. So this change in the surface areas will make the difference in the energy balance and also different atmosphere conditions among the urban areas. So this will make the local urban climates difference along with the things is the temperatures. So the urban areas will temperatures. So the urban areas will receive more heat and also higher temperatures between the them the rural surrounding. And with such overheatings, we have developed a lot of the urban heat mitigation strategies. For example, we have the wide infrastructures. So for wide infrastructures that we can increase the albedo of the roof so that we can reflect more solar radiations from the solar systems. And then we can also increase the wall albedo and the road so that we can cooling the cities by using these wide infrastructures. And we can also use the green infrastructures. For example, we can plant the tree, grass, and also have some planning on the greening areas like the park in the urban areas so that we can control the heat. And we can build up some blue infrastructures, like including the brickwork, wetlands, and also the lake in the urban areas. Now we have a lot of these strategies, but before doing the implementation of such strategies, we need to do the evaluation. So one of the most useful functions or application of the CRMU community land model urbans is that we can do the evaluation by running such model with the implementation of such strategies. And then we can get the evaluation results from the simulations and reflect back to the real world. But running such a model, we all run the CRM in this working group, we must confront lots of the problem, including the installations of such a model. Like it needs a lot of the requisites on the software and also operating systems. And also we need a lot of the case configurations. And also if we don't know how to do the numerical modeling or how to run the computer lab model, the data source to get the data inputs, that will be a very difficult for the outsider of such people that do not familiar with that process. So we develop a universal tool for the urban climate modeling. So this universal tool including two parts. One part is the CRMU app. CRMU app is the CRMU container that contains everything needed to run the CRMU model. For example, this application have including the CRM environment and also the source codes of CRM, including the CRMU. And then we can run such image applications on different software container engineering and software engine like the Docker and also the Singularity. And this image application supports the different OS like the Linux, Mac OS, and also Windows. And it also support different personal computer platforms. For example, we can run it in the AMD and also the ARM platforms. And then the other part is the PyCRMU app. It's a Python interface that can interact with the CRMU applications. It helps us to make running such a simulation become easier. And here is some example of the PyCRMU app. And here's a Python workflow. For example, we can only do these two steps by easily running a simulation of CRMU. And one is we do the initialization, like this code, and then we do the configurations and run CRMU simulations by specifying the case name, surface data, forcing data, and also the run start dates with different simulation lengths. And this code will return a list of the results from CRMU or CRM. And here is some tools for helping people to run their own urban climate simulations. For example, we can use the gap forcings. And the gap forcings help people to generate the forcing input for the CRMU from ERA5. And by specifying the location and also the dates, and we can get forcing inputs from ERA5 and with format of the NetCDF, and then we can generate the surface data for the model input. And the surface data is simply mapping from the ready data in uncast services, like the urban surface data and also the soil texture and data. And then we can directly modify different surface parameters by using this function. And one of the useful things for CRMU is that CRMU sometimes can provide better urban temperature examinations. And here I compare different sources of the air temperatures. For example, for the green line is the AI5 air temperatures, and this line is the CRMU, and then the pink one is the air temperatures from Manchester Airport observational data, and the blue one is the UKCP example predictions. So we can find that the CRMU simulation can provide a better estimations than the raw EI5 data with the airport observational data. So we can see airport is lower developed or built up districts in Manchester, so it can see as a lower developed urban areas. So that this is why CRMU can provide a better examinations for the air temperatures rather than the EI5, which did not include the urban process. And the second one is we can use this application to easily doing the urban climate adaptation evaluation. So here is an example for the white roof. And for example, we can compare different experiments. For the default experiments, we run a cell simulation, and then we change the roof albedo and to see how these strategies will affect the local urban climate. And this plot is so how the cool roof will affect the local urban climate provided by PyCLMU application. So the y-axis is the canyon air temperature difference. So the temperature difference is the cool roof experiment results and then subjected by the default experiments. And the cool roof experiments is that we add the roof albedo by 0.2. And then we do these experiments with different scenarios. So the blue one is the original, and then the green one is that the warming scenario. So for the warming scenario, we directly add 1 degree in the forcing temperatures, and so that we can see how the cool roof will respond to this warming scenario. So we have find that the cool roof can provide a greater benefits at rooms, and also under the global warming scenario, it will provide a more cooling benefits. So here is some potential engineering adaptation. For example, we can use the new materials, the blue infrastructures, green infrastructures, and also we can do the anthropogenic heat controls by using such applications of CLMU app. And here, I want to suggest something I'm doing. For example, I'm doing the heating and air conditioning and ventilations of such heat control using reinforcement learning with PyCLMU app, and to see how such strategies will affect the local urban climates and the energy systems. And I'm also doing the roof sprinkling systems, which is implemented in PyCLMU app, and with the rainwater tank implementation, and to see how these strategies will impact the roof, the water energy losses of the roof, and also how such strategies will affect our local urban climate. And such engineering adaptations can make better urban environments in the future. And for the last one of PyCLMU app is that we can easily do a large simulations for the optimization and also sensitivity task. For example, we can have a lot of the parameters sampling from the CLMUs, and then we can make it very easier to parameterize a lot of the simulations with such different parameters using the Python interface. And with different sampling algorithm like the Lighting Hypercube sampling algorithms, we can generate a lot of the data by PyCLMU app, and then we can, based on this data sets, we can do the surrogate modeling, and then we run a lot of the optimizations algorithms on the surrogate models and get the optimal urban adaptation planning, and also test the urban surface parameter sensitivity. And the last one is that is the tutorial and also the paper we published related to this research. So this is all my presentation. Thank you.
Great. Any questions for Junyu? There's lots of people snapping your QR code. It's a good sign. Yep.
Just a quick question. What kind of container are you using? Docker or Singularity or something else?
Actually, in your personal computer, I think Docker is better. But for the HPC, Singularity is good. But it all supports this software.
Thanks.
Other questions?
Curious if you could speak more to why there's a bias in the middle of the day between the ERA and the urban model. In one of your slides, if you go back, Yeah, that one. What is going on like physically to lead to the bias there?
Actually, I don't know. I think the most bias may come from the AI5. They don't include the urban process or maybe something others because airports observational data it only represents a point, but AI5 represents a region, and we run the simulations of CRM you getting from get the forcings from also from AI5, but the ACRMU's function is that we pass the urban physics uh, of the AI5 source data so that you get a more realistic urban physics or urban process and then have a higher temperatures than the raw AI5 data. So actually I don't specifically know why about your question. Yeah.
One more question here.
Thanks. Great talk. So I was just wondering, with this container, is there easier way to do, say, like play with the code? Like if I want to do any simple code modifications to test some functionality, is it possible to do so?
Yes, and actually, if it will create a link between your personal computer and then the container, and so there will be the source code that if you modify the source code and then you put into the directories of the I don't remember, but you can put it into the build. After we build our cases, we can put after we create cases, we can put the source code into the source of point CRM, something like that. We can put the source code into that, and then you can build.
All right, great, thanks. We're going to transition into the room now, and so for anyone who's going here, you'll notice there's no screen for you to look at or advance slides, so you get to do it all with this and stare up at the screen. For presenters, there's a button on the top of this control that will let you do a pointer, so you can point to things on the screen, and then the big button advances your slides. Next up, Peter Lawrence will talk about the work that he's been doing.
Great, thanks, Will. So I'm going to continue on some work that I presented at the Winter Land Model Working Group meeting, which is looking at using CSM in an emission-driven space. And what we mean by emission-driven is, like, instead of having the concentration of CO2 and the aerosols from fire and biogenic sources being prescribed in the model, we're allowing the model to run freely, given fossil fuel emissions and the fire model burning the natural and crop vegetation, and then the volatile organics coming from the vegetation. So one of the things is, in the winter meeting, I took us through this configuration and what was called the HOPE simulations, which are following the CMIP6 historical and then future projections for SSP 119, 245, and 370. Here we're going to take this framework and apply it into a global tipping points area, and then also into climate interventions. As we're sort of building this project up, we're getting a larger and larger number of people involved. So I'm not going to go through all the people involved here, but it's a growing group, and this is a community these are community projects. I'm going to give a little bit of background on, if you weren't here at the winter meeting, or just to give background to this and see what it looks like. And basically, we're configuring CSM. We're using CSM 215. So this is an older version of CSM, which is used for the large ensemble 2. It's been expanded to have this capability so we can have the emissions being prescribed, and then also the fire and the volatile organics working with, and we also have land surface data sets that are consistent with CTSM 5.3. We have a background. We have these 5 historical ensemble members that run from 1850 through to 2014. They come off this pre-industrial control. It's also configured this way. And then we run out through these highly optimistic projections ensemble along those three trajectories. We're then taking this framework and then applying it for tipping points, which is part of this global TIP-MIP project, the system modeling component of that. and I'll explain that a little later. And also the community climate intervention strategies, we're looking at different climate interventions applied in this framework as well, which Michael brought up this morning. Just to give you an idea of the complexity of what's being modeled right now. So this is a fully coupled model, so the oceans, the land, the sea ice, the atmosphere are all coupled. We also have in the land surface all these activities being prescribed through land use. So we have forestry and pastures and crops and unmanaged areas. So they all have CO2 being exchanged, they have water, energy, the normal sort of things you would see. But then we have both the volatile organics coming out here, and we also have the fire coming out here. Just as a recap, the model on the left-hand side is the fully coupled model with the CO2 and the aerosols being modeled. On the right-hand side is lens 2, where they're being prescribed. The black line here is the historical period. We can see that the patterns of warming over the historical period are very similar. What happens is that the model actually starts off slightly cooler, closer to the HAG crew data, and then ends up cooler over the historical period. We end up with about the same amount of warming through that period. If we look over SSP 370, which is the large ensemble 2 as well, and we can look at the absolute temperatures, which is this plot over here, we can see that we start cooler, and we end up slightly cooler with the fully interactive. But if we look at the deltas rather than looking at the absolute temperatures, so I'm just going to do this one here, you can see that basically the model in these two configurations has a very similar temperature response. So then moving on to the highly optimistic projection ensembles, what we're trying to do is think about how can we get away from a global, how can we hit Paris targets of 1.5 to 2 degrees of warming? And that requires a large number of different mitigation elements that come into it. So if we go to a high level, what we can see here on the right-hand side is this is the temperature response of the historical period, SSP 119, which does this overshoot to 1.5 degrees and returns to current day. We have 2.45, which ends up having around about 2.5 degrees of warming. And we have 370 has about 4 degrees of warming. This is consistent with the large ensemble and our CSM2 simulations for CMIP. Down here we can see the CO2 pathways, which are being modeled by land sinks, ocean sinks, emissions, and we see that we can reproduce those scenarios, both the historical and the SSPs, really well. We don't actually have an SSP 119 concentration pathway because that wasn't one that was prescribed for the modeling suite, but we can reproduce that in an emission-driven sense. One of the key things that came out is that we have the strong cooling in the North Atlantic in all of these models. So we can see that that's primarily been driven by the shutdown of AMOC, the slowing down of AMOC. And even in the SSP 119, where we have this overshoot and return back to current day temperatures, AMOC doesn't recover to the point, so we end up having this cold North Atlantic here, which is actually up to 8 degrees colder than the current day. Okay. Moving on, this is just precipitation changes. We can see precipitation changes. These are very similar to those that you would have seen in CMIP 6. Basically, we end up with drying over the Amazon. We see this large shift southwards and intensification over the central Pacific. And we see this warming, this drying over the Atlantic. Okay, let's go on. So having built the system and having this framework in place, it's been really, it's a very powerful system to be able to start thinking about tipping points. By tipping points, what we're really talking about is systems in the Earth system that once they go through climatic or human-driven thresholds, they change. There's a non-linearity to that change, and so that they have a hysteresis. They don't return back along that pathway. Key things for this, the TIPMIP project is looking at AMOC, which we just talked about there. So we've got AMOC shutting down and saying, is there an irreversibility in AMOC? The other one we have is like looking at the tropical forests, so the collapse of the Amazon, greening of the Sahel potentially, and then the shift of boreal forest northwards. So we took CSM, this framework, and we've got this idealized experimental design, which is this top left area here, where we were doing this warming up from pre-industrial. We do this by giving 10 gigatons of carbon fossil fuel emissions over up to 2 degrees of warming and then 4 degrees of warming as the global average temperature. At that point, we then go to a 50-year period where we have zero emissions, a sort of a stabilization period. And then we ramp back down till we get back down to pre-industrial temperatures. This is similar to what was happening in the flat 10 simulations, but instead of being carbon focused, this was a temperature target driven. And it took us 115 years to get to 2 degrees and 230 years to get to 4 degrees of warming. One of the other interesting things that we sort of find is that the CO2, if we look over here on this other side, so we have this ramp up, which is kind of straight ramp up. But once we go into zero emissions on those two stabilization periods, we see that the oceans and the land are drawing that carbon back down. And then we can draw down carbon again. To get back to pre-industrial temperature along these pathways and these transient pathways, we actually have to go below the 280 ppm that we started off in pre-industrial times. There's some really unusual things that happen in this period here as well. You can see coming down the 4 degree where we have this sort of plateau in cooling as we're ramping down CO2. A lot of this is ocean driven in terms of the AMOC restarting and going forward. Okay. Another component of looking that we sort of identified was looking at the vegetation experiments and what was happening in terms of if you're in this idealized situation, what would happen if forest changes happened at the same time? So the first one was looking at the collapse of the Amazon. So what we're doing is like full dieback of the Amazon back to grasses. The second component was looking at the Sahel, where there's this greening, this great green wall it's called, where there's actually deliberately planted vegetation. And the third one is looking at boreal forest shifts. So basically this northward shift of boreal forests as we warm. I'll take you through quickly the Amazon rainforest collapse. So what we did is we were following the land use modeling and comparison global deforestation scenario. But instead of deforesting globally, what we're doing is just focusing on the Amazon. And we're doing a 2% reduction in tree cover for 50 years over this. So you can see in the top panel here, we have like full pre-industrial Amazon tree cover. And this is 25 years in, we end up with we halved that, and then we're down here at zero at year 50. And they're being replaced by grasses along that process. So what's really interesting is if we compare this 2 degree warming with and without the collapse of the Amazon, we can see that there's a strong warming, both globally and also locally. So we have up to 0.7 degrees global increase from all the carbon that's released from the collapse of the Amazon. That's like 203 petagrams of carbon, which is a large amount of carbon, that increases atmospheric CO2 by 65 ppm. We also see that there's strong drying and warming in the actual area of deforestation, of collapse. So in those areas, the temperatures can be 5 degrees warmer in the collapsed Amazon versus the intact Amazon. The bottom plot here, precipitation, you can see there's drying of that area and actually increases in precipitation across the Central Pacific. I'm going to shift gears now and talk about the community climate intervention strategies. This is ongoing because the models are still running. But what I will do is quickly take you through the experimental setup for these. So this is a reforestation, a maximum reforestation scenario that we're doing, so that as we go through from year 2025 through to 2100, we have this ramp up of forests globally. We've got this constraint so that we maintain agricultural areas, we maintain urban areas. Protected areas are not changed, so we've got the global protected areas database that we don't allow vegetation to be done on there. We're also looking at bioenergy crops, so this is Yan Chen's work, where we're putting in both miscanthus and switchgrass along similar, we haven't got those experiments quite sort of set up yet. And finally, we're looking at stratospheric aerosol injections, and this is the ARISE simulations. We're taking the stratospheric aerosols that have been calculated within this project and putting them back into CAM6. And we're getting this to work so we can get the same cooling in the low-top CAM6 model as you would see in WACOM. And you can see here, we've extended these out to 2100 because they only went to 2070 in the ARISE simulations. And I'll call it there. And yeah, unfortunately, the climate interventions work is still running.
Great. Charlie, go ahead.
Yeah, in the TIPMIP runs,
Yeah.
it looked like you had a positive ZAC in both the medium temperature and the high temperature. And, in the 1% per year, yeah, that one.
Yeah.
Is that right? Are you showing a positive ZAC there? And if so, why? Because we, in both flat 10 and the 1% per
Yeah.
year, we get a pretty strongly negative ZAC. So what's going on?
So you mean in terms of temperature response there? Yeah.
The orange and the light green.
Yeah,
Like,
so-
particularly the light orange.
Yeah, and I can't tell you why they're different from like the flat 10, but I can tell you that it's ocean heat content re-emerging at that point. Fred Costera has done a lot of work in the ocean heat content and AMOC. I can't tell you exactly. I mean, the orange line is pretty flat. That's
It's positive. In the flat 10 for CSM2, it's quite negative.
it's
It's money to lose about a third of a degree.
a third of a degree, like over that 50-year flat period. I don't know. This is configuration. They're configured exactly the same way as the flat 10 simulation. So I don't have an answer for you, Charlie, but it's obviously something we'd like to look into. The purple line was one of the ones we're really most interested in. It's like this really strong non-linearity. You're still drawing down carbon. And I don't know, we had to go to 115 years and 230 years to get to these 2 and 4 degree points. So there's more carbon, slightly more carbon than flat 10.
And you see something similar to that in the SB534 overshoot, but after year 2200, you see a really strong unforced warming
Right.
in CSM2 as well. So it's probably similar dynamics.
And I took a lot of the slides out, the ocean slides, because it's the land meeting, but I did have ocean and AMOC slides here, but I took those out. I'm sorry. Yeah.
And Peter, a really awesome talk, really amazing framework. I guess my question is on the Amazon deforestation piece.
Yeah.
It was really strong, and there was a synthesis of kind of model experiments of deforestation in the Amazon, led by a group in the UK, and then also LUMIP also did experiments that are somewhat similar, maybe not identical,
Yeah.
but this strikes me as being like a couple sigma higher than the LUMIP. But have you compared it physically to that, and what might be going on compared to the earlier like CLM2 to get like a 5 or 6 degree change there?
In terms of the temperature response?
Yes.
The temperature response, I'm not sure about. I think it's pretty much all hydrologically driven. You can see the decrease in precip and the feedbacks, probably cloud feedbacks. The carbon is that this is comparing a 1850 Amazon vegetation cover at 2 degrees warming. So it's,
Carbon seems good, just the temperature really and the water changes.
right.
More.
Maybe I'm not sure exactly. Like this were very hot off the press. Like I haven't done a lot of delving into the componentry of it, but this is this is 30-year climatologies at the end of, and we did do this long sort of. We did the 50 years to to have the degradation of the forest, and then another 50 years of stabilization after that. So yeah.
More deforestation than
Yes, yeah, and LUMIP was only, 30%, right, I think, or 20. Yeah, that's exactly right. And it was a patchwork in LUMIP.
Great. Let's thanks Peter again. And Charlie Coven will talk about fates and land use coming up next.
Cool. Yeah, so I'm going to talk about some fates, land use stuff, and which is like Peter's, also a continuation from a talk I gave on the Land Model Working Group. I had hoped to make, I hope this would be, I feel like I've been giving the same talk versions of this for a while now. So I apologize, and I hope this would be, I would have it all figured out by now. And I'm getting there. But okay, so what's this about? So this is, yeah, so putting land, transient historical land use into fates. And so just some brief sort of recap for context. Yeah, I'm not going to go into what fates is, other than that it's, fates is the sort of next generation vegetation model that includes disturbance as kind of a key, like a key feature. Is it's resolving the disturbance legacies. Because fates resolves disturbance legacies, it's got a sort of different representation of land use. And specifically what it's doing is it's treating land use as it's sort of at the same time that it's treating natural disturbance. So basically, with fades with land use on, there's 4 types of disturbance. You've got like tree fall, which is like individual trees dying of carbon starvation or hydraulic failure or whatever. You've got fire, moving across the landscape and burning, and sort of creating, a burned area and then an unburned area, which then proceed along 2 separate trajectories. And then land use is similarly, we've got tree harvest where you harvest a certain fraction of the grid cell and you leave the rest of it behind. And the part that you harvested, you carve off into a new patch and it has its own separate trajectory. And then land use change, which is, sort of being driven by these kind of land use data sets from originally LUH2, we've now just most recently updated to LUH3 for CM7, but it's effectively the same thing. And so what this does is it creates this disturbance matrix where we've got labels on each patches. So they have a land use type, and so within each of these, within this matrix, you've got land use change is basically all these off-diagonal elements that you change the land use type. So you've got a land use that's a patch that's, say, a primary land use, and you change it to pasture land or from pasture to secondary harvest. And when you harvest secondary lands, you create a newly younger patch, and when you harvest primary land, you create secondary land. So the point is that the land use itself is directly driving the disturbance regimes in fades, rather than being mediated through this land cover step. And okay, so first I want to talk a little bit about the spin-up problem, right? So FATES is structured around this, tracking disturbance history. How do we capture the disturbance history that had occurred before the start of the simulation? And what we've been working on, these kind of 2 separate approaches for how to deal with this. One is that you spin up the land model with no land use change at all. So you just assume everything's primary land. There's no anthropogenic influence at all. And then you apply, at some point in the model simulation, you apply all of the prior disturbance that's required to get you to the land use state at the time of starting. So if you deforest all of Europe, all of South Asia, much of East Asia, kind of, in this, like, initially on in the model scenario, in the start of the model, in order to create the agriculture and the mosaic of land use types that's there at the start, before the start of your simulation, and then you run a transient simulation after that. The other, and I spoke a lot about this, in my talk at the Land Model Work Group meeting this spring, is you calculate a set of harvest rates that gives you a secondary land age distribution that best matches what you would get in the full transient simulation if you were to start it like 1,000 years ago. And then you spin up the model with primary land, with everything in the initial land use types plus this additional harvest rate that gives you the correct age distribution. So that then at the start of your run, you've got both the correct distribution of land use types, as well as secondary lands are disturbed more strongly than primary lands because you've got this harvest, and then you can kind of proceed through that. And this is sort of most analogous to the way things are done currently in CLM, except that we're trying to calculate the age distribution of secondary lands as the thing that we're targeting. Okay, so I've been doing a bunch of experiments trying both of these things. And so for one thing is, one basic question is how long FATES even takes to spin up. That we've, because we haven't really been running the model in these sort of global transient simulations, and so there's just basic stuff we're trying to figure out. And so here's just an example from a spin-up run with AD spin-up on. This is showing the global net biome production, annually smooth for runs. And first of all, you see kind of some weird behaviors. Oops, sorry. Let me go back here. You see this weird little It's not like a monotonic decrease. In CLM, when you do this, it basically, if you plot it in log, like the log of NBP or the log of the absolute value of NBP over time, it basically is a straight line. Here we see this weird thing where you kind of get to 0 NBPs. You think you might be spun up, but you're actually not. You go back out of it. This seems to be being driven by the tropical forest, and I'm not even totally sure I understand what's going on there. But the point is, after about 300 years or so, you get to where things have settled down. You get this long-term 0 NBP. And I say this is like the simplest configuration. No nutrients are on here, this is how long it takes to basically get the vegetation and soil carbon equilibrated in this. Okay, so then what happens when you run this in the transient case? Okay, so this is a figure that I'm sort of happy to have been able to make. What this is showing is the total area of the planet in different land use categories over time. And on top of that, the age distribution for primary and secondary lands over time. So the black lines is actually coming from the forcing data sets. And unfortunately, I've chosen pictures or colors here. The crop and pasture and this thing are the same color in the original version of the figure. They're different. But the point is that like each of these land use types, the color blocks are lining up with the straight lines. This is kind of a sanity check that the driving data set, the black line is just the driving data set. So that's just like if the model is working correctly, the colored blocks should be lining up with the black lines. And now they are. Originally, as of when I tried to do this in the spring, they weren't. But they are now. Everything's sort of lining up correctly. And so the color blocks is lining up with the lines. So the input and the outputs are working. But then you get this extra information, which is the age distribution of both the primary and secondary lands over time, sort of emerging through the interplay of anthropogenic and natural disturbance. So one thing you see because of this, so this is the way where we sort of impose all prior land use at the start of simulation. And what you see when you do that is that, initially all the secondary land has a 0 age distribution because you've just deforested all of Europe in order to create, this initial conditions. And then over time, that the secondary lands kind of the age structure then recovers, right? So after something like 100 years, you get to a more steady state age distribution. If you do the same thing, but now starting with this spin up where you've applied the secondary age, the harvest on the secondary lands initially, you end up with something and so now you can actually just start at 1850. You don't have to do this extra 100 years of spin up. You start off where the secondary lands now already has, roughly the same age distribution as you see in this transient simulation. So to first order, it's basically working that you can get a similar age distribution. It's not exactly right. It looks like there's slightly more young secondary lands in the steady state spin up. But to first order, it's giving you sort of approximately the right age distribution at the start of your simulation, which then sets things for the transient simulation after that. And now let's switch to talk about carbon. And here, the reason why, unfortunately, this isn't the last version of this that I'm going to do is that I realized after this is done that the C3 grasses were basically all dead in this run. And so which is an issue of model calibration. I was using a version that just had the C3 grasses weren't well calibrated. I've been working on this since subsequently. We've got healthier C3 grasses, and so I'm redoing all this right now. So that's going to amplify some of these differences between these cases, but I still think there's some useful stuff that we can get out of these simulations. Okay, so what is this? So this is the full global land carbon budget in 3 cases. One with this sort of constant 1850 start, and then these other 2 over the 1750, starting from no land use and starting either 1750 or 1800 and going forward. And so you see in these ones where we do this initial deforestation event that you get this big pulse of carbon that's basically in product pools because you've just deforested a large fraction of the world, and then you kind of things need to re-equilibrate. The blue and the green line, they come back together, about 120 years after the start of this one. So this is starting at 1800, and so these 2 lines are basically they don't reconnect until about 120 years after the start of the blue line. So that tells you that if you're going to do this thing where we start up with no land use and then apply all land use at once, it takes about 120 years for that initial pulse to work its way through the system. And again, this isn't carbon only. That'll probably be worse, or almost certainly be worse if we turn nutrients on. But the yellow and green lines, after the period here are kind of running in parallel. But I'll get into, a little bit more. So, okay, so this is if you break the total global carbon into the different pools. So on the left is the wood product pool, where again, you get this initial huge pulse because you've just deforested a big chunk of the world in these two sort of early start cases, versus the constant 1850 where you don't create that initial pulse, which then decays away pretty rapidly. The vegetation carbon, between the cases, again, there's about 100 years that it takes for the blue line and the green line to reconnect after the start of where the blue line is. But then the yellow line and the green line, so the constant 1850 case, and then the early deforestation and then subsequent transient case they follow each other pretty closely. And the big difference is in the soil carbon, right? There's just this huge offset in the soil carbon that persists, and a lot of that has to do with the fact that in the simulation, because the C3 grasses were dead, their inputs into the soil carbon were less. And so I think this difference between the constant land use case and the no land use spin up case is partially an artifact of the fact that the C3 grasses were very dead. If we just sort of line everything up to the carbon stocks of 1850 and ask, okay, what is the transient carbon change in this case? You see that the two cases where the potential vegetation that the potential veg that's starting early kind of drops off faster than these other two cases. And basically that's because it's trying to lose the carbon that the yellow line, because it's starting off under this constant 1850, you're starting off with much less soil carbon. There's therefore less carbon to lose when you turn on the land use. Whereas the other ones are trying to lose carbon in order to equilibrate the carbon inputs with the land use cover. And so basically then, if you look at these in a sort of derivative sense, again, you see that the slope of this yellow line is showing less of a sort of inferred land use emissions. And this is basically just calculating this as the derivative of this one, right? So this derivative here has a lower slope, and so basically it's saying that we're losing less carbon from the soils than these two. And again, you can see that here in that it's losing less carbon because of this soil carbon. There's less, it's losing less carbon to the soils than the other ones. And again, this really just speaks to these like really long-term legacies of these spin-up conditions, right? These decisions you make about how you equilibrate the model, they don't go away; they persist in time. Okay, so just to summarize, basically just like doing the spin-up itself in phase requires about 300 years to reach steady state under this current approach. And this is like the simplest version, carbon-only dynamics. It'll get slower when we turn on nutrients. But that's roughly what it takes to get a sort of couple of vegetation soil carbon that's a steady state. The vegetation carbon dynamics between these two spin approaches are relatively similar after about 100 years of transient dynamics, but they lead to really different outcomes, particularly for soil carbon. And these persistent soil carbon differences lead to long-term differences in the inferred land use change flux that just persist in time, even out to the present. Partially, this is going to be an artifact of the C3 grass issue in this particular run. So hopefully rerunning it, and this will partially, I expect, go away, but I don't think it'll fully go away. I think that this is pointing to a real thing, which is that soil carbon has huge memory, and these decisions about how we spin up the model have long-term implications in the persisting carbon budget. Which then begs the question, which approach is more realistic, right? I tend to think that both of these two cases represent kind of an end member approach of like, you assume you can kind of apply all the history all at once, or that everything's fully equilibrated to this long-term history. Reality is probably somewhere in between, but I think this constant 1850 approach is likely more realistic because it allows this kind of deficit in the soil carbon to already be present. So the model is not then trying to bake that in during the trend dynamics of the historical simulation. And then the next steps, we're currently rerunning under a slightly different regime with healthier C2 grasses. We've turned on grazing, and now there's something for the grazers to eat because the C2 grasses. We're updating the forestings from LUH2 to LUH3, and I'm going to follow something closer to trendy-like protocol, varying both climate and CO2 so that we can calculate these things in the presence of these other things. But then otherwise, the land use machinery itself seems to be working. And then once we're done with this, we can start to do this more formal benchmarking using things like ILM that takes into account the land use. So I'll stop there.
We'll have time for questions after this next talk. Some time for discussion. So you can kind of see already with the kind of scope of what we've heard about already this morning, from urban model developments to emissions-driven runs, and now FATES, that the Land Model Working Group is kind of tackling a whole lot of things, which makes it my job fun, because on any given day there's a literal or figurative fire in one of those pieces of code, and so it's exciting to try to figure out what's going on. So this is kind of the overview talk. I want to touch on Dave touched on some of the things that we've been doing in CESM, and I wanted to give a little bit more of a land model focused to what's happening in CESM, and then also for the CLM6 release. So just kind of to remind us that the kind of 3 or 4 big questions that I think the Land Model Working Group is trying to figure out is, basically where are we going to put the carbon, how do we grow the food, and are we going to have enough water to meet those needs? And then increasingly, because of the urban model developments, also thinking about some of the kind of human impacts from climate change in urban systems. And then kind of on top of that, there's this nod to predictability and thinking about how we can help inform actionable choices that get made on kind of sub-centennial timescales, which is kind of historically has been the purview of CESM. And so along with that, I think there's a few features of CESM that I'm really excited about for the CESM 3 release. And so one of those is having emissions-driven runs, which are core to the CMIP 7 fast track experiments. Along with that, I think the work that Peter's doing and allowing us to have interactive fire in those emissions-driven runs is really exciting to start getting some of these fire climate feedbacks. In CESM3, we're interested in having interactive land ice, and so what happens on the ice sheets really matters, and that a lot of the land model physics comes into play then. And then finally, Linnea will talk after the break about some of the parameter uncertainty work that she and the PPE team are doing. And I think that really just kind of throws open the door. Like when you put all of these together, there's a ton of really exciting science that we can start to do. Okay. This is also a fun slide to make. I went back to last year's talk and looked like we had kind of a short list of things that we thought we had to do, and then a longer list of things that we wanted to do. And then it's even a longer list of what we accomplished between last year and this year. So I'm not going to run through all of these, but I'll throw just kind of a few shout outs. So we have a new dust scheme that Danny put in that's been merged into CESM. The matrix CN branch was this long tail branch that's really critical for the PPE work and has finally been merged. So thanks to Eric and Sam for bringing that in. Fire model updates. Fang Li has improved some of the capabilities of the fire model, and she's kind of actively working with us as we parameterize for CLM6. There's some new crop calendar work that'll allow us to grow things like rice in India, which we know is for real. So thanks to Sam Rabin for getting those in. We've got new Plumber 2 capabilities we'll also hear a little bit about today, some Mozart improvements, Megan BVOCs, and then a whole lot of kind of more software infrastructure that's going on. I want to call out the snow thermal connectivity scheme. That'll come up in a second. Some of the work that we're doing in CESM 3, and then also the new data sets that we have. So we've for the longest time, we just had one set of surface data sets, and in the last 14 or 15 months, we've made 3. We've gone through this 3 times now. So we had 5.2 data sets. Now we have 5.3 data sets. And I've tested the 5.4 data sets to make sure that they work. And those 5.4 data sets have the CMIP7 land use, land cover change data incorporated in them. So those are kind of ready to go. So huge thanks to the software engineering team, both on the CLM side and on the FATE side, for getting a lot of this work done. And then a number of other folks that are shouted out here who made these capabilities happen. Okay, so Dave talked a little bit about this, and I think it's important, so I wanted to throw a little more light on it. Adam Harrington noticed 6 months ago that the CESM, the melt that we were seeing over Greenland in CESM2, looked kind of reasonable, and that what we're calling here the CESM controls were really high. So Greenland ice melt was way too high, which is a problem if you want to run with interactive land ice. So we went back and added what we're calling, this is the old snow. So we reverted a bunch of the snow changes that we made for both Arctic vegetation survivability as well as some permafrost metrics. So we could revert to the old snow and get something that was CESM2-like. And we figured out that a big piece of that was related to this switch in snow thermal connectivity. So when we turned on the STERM scheme, which is what we're using in CLM6, a big source of that bias was because of STERM. And so what we're doing now is over glacier land units, we're using the old scheme, which is called Jordan. And over vegetated and lake land units, we're using the STERM scheme. We're using STERM. So now there's these nameless changes that you can switch between STERM and Jordan. It's not that big a deal, but it is a little funny that we're using different physics over different land columns, but that's what we had to do to save the Greenland ice sheet. Along with that, there's also a change at the parameters upper limit of destructive metamorphism, and that's been increased from, and I don't even know what the units of this parameter are, but it was 100 in CLM4, 175 in CLM5, and now it's 250, so we're just kind of keep turning it up. But if anyone's doing single point runs and looking at snow, these 2 changes to snow thermal conductivity and then this upper limit of destructive metamorphism of snow are really sensitive parameters for getting snow depth, snow density, and soil temperatures right. So they really change things in ways that are worth knowing about, I guess. Okay, so the other bias that we have is this tropical precipitation bias that Dave mentioned. You can kind of see there's this almost, I don't know if you'd call it a dipole, but there's a dry bias over the Amazon and a wet bias over the Sahel. This is something that we spent a long time trying to investigate, and we couldn't reproduce it in any F cases. So when we take out the ocean model and are just focusing on land and atmosphere, we don't see this, so that's what oops, this is gonna get me every time. That's what's shown in this upper left panel. And then in a historical run for a CESM3 run, as well as 2 1850 runs, we've seen this. So some runs that Gustavo did just before the computer went down a couple weeks ago show some promise that we're able to address this bias. But this is one of the things that we might have to think about ways to either live with or work with as we finalize CESM3. Mostly because when you're missing this much precipitation in the Amazon, it's hard to grow an Amazon rainforest. And so if you want to have a coupled model with an interactive carbon cycle, we need to kind of figure out the balance between dealing with some of the underlying climate biases that we might be living with, and then also having trying to run with as robust a carbon cycle as we can. So again, this is kind of TBD, but something to be aware of, that current versions of the model are having this problem. I'm super excited about some of the post-processing tools that the Cupid team has put together. And so what I'm showing here, it says CAM diagnostics on the top, but you'll notice that this isn't a CAM field on the right side of the screen. It looks like I pulled GPP here. So this is annual GPP from comparing a CESM3 test run and a land-only run. Really doesn't matter what the simulations are. It's just exciting that we have kind of this new post-processing tool that you can start looking at the data for. So this was built kind of branching off the ADF framework, which is the atmosphere diagnostics framework that Justin and a bunch of other software engineers and folks in the atmosphere model working group have been working on. And we've kind of taken it. We've had one or two hackathons where people have committed some pull requests to add some new features. And all of this, as of Thursday last week, was wrapped into another PR that's bringing the ADF or bringing land features into Cupid. And so pretty soon, when you get a CESM checkout, you'll be able to run land diagnostics through Cupid. And they don't aesthetically necessarily look really pretty, but you can open up a pull request to give us better color bars or better color ranges or whatever it is that kind of to change these default settings. So a huge shout out to folks that have worked on this. And it's exciting to kind of have this capability here. The other thing I'll note is that KM is now trying to figure out how they can not have to regrid their data. They were going from the NE30 grid, which is unstructured, and regridding on the fly before writing out their history files to an FO9 kind of standard run, standard, or, you know, a gridded output. But luckily, the ADF group can pull from the land diagnostics because we already have that capability. We can plot with unstructured grids already here. So that's kind of a nice back and forth that we're able to do because this collaboration has been pretty tight. Okay, Linnea is going to talk more about this after the break, but I just wanted to talk a little bit about some of the CLM6 calibration that the PPE team has been doing. And so this is just an example of trying to calibrate to 3 metrics, so LAI, leaf area index, GPP, and total vegetation carbon for a single PFT. And so the benchmark targets for this is for tropical rainforest, are shown with the blue dashed lines, and then there's some uncertainty around those. And so what's shown in gray is the Latin hypercube sampling that's been done over successive waves as part of the PPE project. The black point is the default calibration that we had, or the default we had from CLM5, or actually, I guess a CLM 5.3. And then the calibrated full grid and sparse grid are shown in the orange and teal colors. And so this is just to show that we're able to use the PPE infrastructure to start calibrating our model kind of in biome-specific ways to these observational targets, which is quite exciting. And so a couple weeks ago, I ran a baseline simulation plus 5 candidate parameter sets that Linnea suggested. We ran all those through ILAM and kind of got a first look at what CLM6 hopefully will look like. So in tropical forests, the take home is that with this climate, it looks really good. In CESM, it doesn't look quite as good. And I should say these are using Crew JRA, which is going to be our default forcing for CLM6. So this is when you look at the kind of baseline version of the code, or our baseline parameters, and then our just one of these test parameters, we're getting, I think this is for max LAI, we're getting much lower LAIs that are kind of more in line with our observational targets. And so this is mapping from the sparse grid that the PPE is using. No, it's not mapping, this is the actual run that we're getting out of a 2-degree run. So it looks great for tropical forests, kind of as intended. But something happened with Arctic C3 grasses and they all died. So it's kind of back to the dry, it's, 2 steps forward, the tropics look good, and 1 step back, Arctic didn't quite map right. Linnea has lots of ideas for why this happened, but I just want to kind of, the PPE tools are awesome, and then it's really good to check them on a full grid again, because sometimes you learn things that are unexpected. So, but this will hopefully be resolved. We've got a case waiting in the queue as soon as derecho comes back on to try to address this. So, all right, a quick slide from Adriana about some of the FATES SP calibration that she's doing. So Adriana did a CLM SP calibration and a FATES SP calibration. SP is for satellite phenology. And she looked at kind of a suite of hydrology, biophysics, stomatoconductance, photosynthesis parameters, as well as, I still don't understand this, but biogeochemistry parameters that are important for FATES SP calibration. And it's kind of, and I shrunk down what was otherwise had a ton of information on this slide to make it a little bit easier, for at least for me to understand, and basically just showing that she's able to reduce some of the biases in GPP in the bottom right-hand plot compared to the default parameterization for FATES SP. And I'll leave this up here because while the machine's been down, Adriana spent a ton of time making this awesome Shiny app to help visualize some of these. And so that QR code will take you to her Shiny app, and you can spend the next half hour kind of flipping through plots and checking stuff out and coming up with questions for Adriana after you look at it. It's super cool. Everyone's got their picture, I hope. Okay. And so then I want to conclude kind of by saying, Dave alluded to the sum, and I think we're rapidly approaching kind of some challenging times for the working group. And over the past round of model development, I think many of us were under the maybe the optimistic hope that we could maintain kind of maintain development on two branches, one on the kind of big leaf version of the model that uses a sunlit and shaded leaf, and then also on the Fates version of the model. And I think that the last couple of years of our model development has really shown that we just don't have the software engineering or scientific expertise to push these two development trains forward. And so at least within NCAR, we've sort of decided that we can't keep maintaining the development on these two fronts. And I'd like to move us as a working group towards working with Fates more, which means that effectively, as of now, we're not going to be able to support further development on the big leaf version of the model. We will be able to maintain that version of the model. And if you look at CLM5, we released that in 2018, 2019, and we're still using that model today. And so we're going to maintain the big leaf version of the model moving forward for the kind of the lifespan of CESM3, but we really need to move to Fates. I think the community, like the Fates team, has shown that there's great promise in using Fates, and so as a working group, we need to really move that way. So that's sort of the, I guess, last comment that I'll make is that we need to pivot to Fates, and so to do that, we can really only invest our software engineering resources for Fates development. Which doesn't mean that if you're a hydrologist and you want to add the Van Gnutschen scheme to CLM and not whatever we're using now, great. Like you can still do that because Fates can use it. But if you're developing a new phenology scheme or new photosynthesis scheme, that needs to be done kind of in Fates, which is I think important to do. So final thoughts in the next. It was great. I got stuck to Jim Randerson and Paul Dermeyer for a little bit on Friday, and both of them had like these really fresh ideas that I think are important for us to think about. So in the next few months, as we're getting ready to release CLM6, having as many of our eyes on the results that come out will be really helpful, just so that we're able to address biases, hopefully, or at least know about them before we release the model. I don't know what I put the map up there for, but if you want to help develop some of the diagnostics, that's great. And then kind of longer term, really pivoting to Fates, I think is going to be an important move for the working group to make. So with that, I think we've got a few minutes for questions, both for me and then also for other speakers that you heard from this morning. Thanks. And I'll try to do double duty and run the mic around and answer questions.
Okay, no, I will. I appreciate your two things. One is the emphasis on Fates and the idea of moving over to Fates as sort of the default vegetation model. I also appreciate that the idea that if you're doing soil hydrology, that still exists within CLM.
Yep.
And so I think it's really, we need to start actually being very clear about what Fates does do and what Fates doesn't do. And for example, another one, I've heard it many times already today, this idea of big leaf CLM going away. You know my thoughts on that, which is that's only for GPP, you know. And energy fluxes or surface energy balance is still done within CLM, even with Fates turned on. So I think we need to be careful about like what Fates is going to do and not going to do, so that the community really realizes where they can focus efforts. So for example, if you're interested in surface energy fluxes and coupling with the atmosphere, that's all on the CLM side. So it's just more of a comment, but yeah.
Thanks, yep.
So the software, TSS software team have been meeting along with the DOE Fates software team to really like lay out the interface between CLM and Fates and what variables are passed back and forth. So we're trying to make that much more clear for us as the developers as well as scientists who want to use it. So that is something that we recognize and we want to make more clear so that.
Questions? I was like sweating about the Fates thing. Like, oh my gosh, people are gonna have so many questions. Nothing. You're just ready for it. It's great. Yeah, Adriana.
Okay, yeah. If you're a student and you want to, like, if you had an idea to develop in CLM Big Leaf and now you're freaking out, you can come talk to one of us because you can probably still do that, or you can pivot to Fates and we can help you do that. Because, yeah.
I guess another thing I'll say is I think another big challenge that we have moving forward is documentation. So I want to give a shout out to Sam Rabin because the work that he's done on our documentation infrastructure, I think will make it much easier for us to document CLM 6. And then I think along with that will become, all of us, me included, becoming more familiar with and then also documenting Fates. It's something that we have to work on.
Just for Charlie, thinking about those different initialization strategies, you've probably told me this before, but trying to understand that when you deriving the harvest fluxes, what do you need to do to get those harvest fluxes, and how much does that factor into the total cost, like to figure out those harvest fluxes ahead of time to drive?
It's just a Python script that figures it basically. So yeah, so there's there's kind of like a toy version of something like Fates that basically just calculates the age distribution over time, and so it runs the starting at year 850 from the start of the land use data set. It tracks the age distribution in this sort of offline sense, and then it just calculates and so it calculates the harvest fluxes that give you the best approximate cumulative age distribution, and it takes 5 minutes.
So that's just a tool that we need to provide.
It's a Python tool. Yeah.
Yeah.
And the NorESM group, Marit in Oslo, already. So I originally done it all just to work on the latitude by longitude grid, and Marit got it to work on the unstructured grid already.
I have a question related to Megan that generates the BVUC emissions, which is also a function of the land cover types. So I just wonder when we turn on Fates, is this in couple with Megan? So we do see the perturbation in the BVUC emissions due to the land cover changes?
I think Rosie's working on incorporating Megan into Fates for NorESM, and so then we'll have to pull that back onto the CLM branch. Yep. Yeah, so that's definitely on the radar. Thanks. Yeah, Peter.
I'm wondering about an NWP version of CTSM. Are we still progressing on those lines for high resolution runs
Yeah, that's a good question. We haven't been working on it. We could think about it for high res runs. Yeah, I think that's a really good question.
Cool. Just leaving it open then.
Yeah, it should work. Yeah.
But I mean, because we have an SP mode of Fates, in principle, that might be just as cheap.
Yeah.
So.
Yeah. Great. I think we're about at the top of the hour. So, Dave, it's picture time. Is that the plan? And then we'll come back here at 3:30 to hear some more talks. Thanks, everybody. Just kind of one piece of, I guess, housekeeping. For folks that are joining us online, there's a Slido link that's open for chats or questions. And so if you're online and you have a question for the speaker, go ahead and type that in the Slido, and then Kaylin will read it for the presenter. Which also means I don't get to pass around the mic anymore, so people in the room, if you have a question, if you can go to the floor mic, that would be great. Cool. So next up, Linnea is going to talk about PPE work.
Okay, great. Thank you. So I have been working on tuning CLM6 for CSM3 with everyone in the community's help and support, but especially Daniel Kennedy and Katie Dagan, who have been integral to this work for years. And I want to just start by kind of framing the ethos that I bring to trying to calibrate CLM. I think we only observe a fraction of the processes that CLM simulates. And so we want to be cautious that we're trying to align the model with these observations, but not calibrate to them at the expense of other processes that we aren't observing, that aren't in our observational databases. So you'll see kind of this ethos manifest in some of the decisions we've made along the way in this tuning process. So this is the project that I usually talk about. You all have seen this presentation many times. But for those who haven't, after there was a code freeze for CLM6, we started to assess parametric uncertainty in the model. We started by running a one-at-a-time parametric uncertainty simulation and selected 56 parameters to run in this perturb parameter ensemble. We then ran a really large Latin hypercube ensemble with 1,500 ensemble members. This is using the sparse grid. It's all offline, so forced with crew, JRA, reanalysis, all similar to Daniel Kennedy's work in their paper. And then we gradually work through these waves of history matching where we introduce observational constraints and hone the ensemble into to fall within the observational uncertainty really gradually. And this is kind of, I think of this as the inverse of calibration, where calibration is looking for a single best parameter set. Here we're actually looking for anything that doesn't agree with observations and ruling it out, and then just retaining all the parameter sets that are left. And so we've worked through 3 waves of this process, and we're slowly kind of honing in this ensemble onto these observational targets for the data sets that we have of leaf area, GPP, and total vegetation carbon. This next wave is going to introduce latent heat and sensible heat as well. But I think what's exciting is that by constraining this parametric uncertainty using variables that we do have observations of, we are able to constrain some of the uncertainty in the cumulative land carbon sink, which is something that we don't directly observe. So we'll continue down this road, but for today's talk, I wanted to demonstrate how we're using this large ensemble to train emulators and then use that emulator for calibration. So emulators are really just any computationally fast surrogate for the Earth system model. We traditionally haven't been able to calibrate CLM because it is so expensive to run in serial, and most calibration methods require a lot of serial simulations. So if we can train a machine learning emulator, which just relates any input parameters to any output of the variable, then we have this really fast, cheap surrogate for the model that you can plug into any of your traditional calibration methods. And importantly, it's differentiable. So the emulators we've developed are quite simple, but we've trained, they can be trained on that large ensemble that's generated from the perturb parameter ensemble work. And we we spent a lot of time coming up with this design so that it would enable us to be able to tune PFT parameters independently. Land models already have a lot of parameters, but when you allow any parameter that has independent values for different plant functional types to vary independently, that blows up the parameter space. So we spent a lot of time designing these biome and variable-specific metrics that allow us to calibrate PFT parameters independently. I'm not going to talk about that too much. They're quite simple. They're just Gaussian process regression, and we get really good performance for these variables that we're trying to emulate here. So then we can use this like small ensemble of emulators for calibration. And that you can use the emulators in any type of traditional calibration that you would use with like a hydrologic model or any other fast model. MCMC, for example, is really commonly used, which is more like a sampling scheme that then you end up with an ensemble of samples from your posterior and gives you really robust Bayesian uncertainty quantification. But it doesn't take advantage of the fact that your emulator is differentiable, and it doesn't scale well to really high numbers of parameters. Different numerical optimization schemes, there's a million of these. These are like genetic algorithms or annealing or particle swarm optimization, things like that. They typically are trying to minimize a loss or a cost function. You end up with a point estimate, like a single best parameter set from these. There's some ensemble methods too. They don't do formal uncertainty quantification, but you can use the gradients, and they scale well to high parameter environments. So we've adopted one of these numerical optimization methods, ADAM. It's adaptive modal estimation, adaptive moment estimation, and we simply just minimize a cost function. It gives us a point estimate, but we can run a large number of initializations of this at the same time because the emulator evaluates one new estimation, one parameter set at the same speed it can evaluate like 1,000 or 10,000 estimates. So we can do this in an ensemble-based method. And then importantly, it takes advantage of the gradients. So these emulators are written on platforms like PyTorch or TensorFlow that are differentiable. And if you construct your loss function in a differentiable framework as well, you actually have a full gradient from the input parameter set to the loss. And so you can backpropagate that gradient. And that allows us to calibrate a lot of parameters simultaneously, and it converges really quickly. And it's really simple. So this is the method we're taking. Using this gradient-based optimization with the emulators, we're calibrating LAI, GPP, biomass, latent heat, and sensible heat. And we're trying to calibrate 195 parameters, which seems crazy, but it's working. Those are PFT parameters varying independently is why there's so many. And then in this way I've constructed the loss function, this is where kind of that ethos of trying not to mess anything up comes in. We start by initializing really close to the default model parameter set rather than trying to do a full global optimization. And then we also introduce this penalty into the loss function that is, penalizes the optimization for moving away from the default parameter set. And then I'm not willing to kind of move too far from the default in order to match the observations exactly. So the loss terms stop contributing to the loss once they're within one standard deviation of the observational target. There's an infinite number of ways you construct this loss, but this method is really flexible, and you can kind of build in your own methodology into this loss function and then repeat it as often as you want. And this is useful because tuning is it's going to be an iterative process. We're going to have to work through this multiple times. And so because we have this large ensemble that we can train the emulators on initially, we don't have to go back to the initial phase when we introduce new terms or new variables that we want to calibrate. You already have that large ensemble, and you can bring any new variables into your calibration with these, by just putting it in the loss function. Okay, so how is this going? Will showed these already, but these are just scatter plots of leaf area on the X and GPP on the Y, with the full Latin hypercube ensemble in the gray points, and then the observational target and observational uncertainty in the blue kind of target. And our calibrated sets are in orange, and then when we run those on the full grid, they're in blue. And so my takeaway from this is just like, it's not that hard to get the model within the observational uncertainty for all these different biomes, because we're allowing the PFT parameters to be tuned independently. This would be impossible if we weren't allowing the PFT parameters to move independently. We still have some pretty big differences between what it looks like on the sparse grid, our calibrated sets, and what they look like on the full grid, especially in the boreal shrubland and Arctic, in the tundra. And we think this is due to our spin-up methodology, actually, so we're still kind of diagnosing why this is. But we can meet our targets, metrics, but just because you meet your metrics doesn't mean that you're improving the model. And so I have a couple things I want to point out here. In general, these are ILAM results for a few different tuned versions compared to the default, and in general, we're improving the variables that we're calibrating, so biomass, GPP, leaf area. This thing is hard to use. But one of the things we saw is that the soil carbon is now really low, so by reducing biomass significantly, we don't have as much carbon inputs going into the soil, so we need to slow those turnover times in. And that just emphasizes the need for these tuning tools to be adaptive, and because this is going to be an iterative process. And then we have some I think we're running into some structural challenges where we are having a hard time in the African savannas of bringing C4 grass up, and so we're kind of trying to diagnose that, not through the PPE tools, but through a more systematic structural approach. So I want to talk a little bit about the challenges. I think metric alignment is big. Just because we're getting the mean state better doesn't mean that this is a better model, right? We want to develop metrics that are more representative of what we as an Earth system modeling community think is a good model. That might be response to forcing, like how does this model behave when we introduce perturbations and things like that. So like having more dynamic response metrics, I think, is going to be important, and especially metrics related to hydrology. We don't have really great metrics there. A challenge for this system also is that this is a perpetually evolving code base. And so we can't just run this really large experiment and have that be our only version, and then as soon as a new parameterization comes in, all of that is kind of not representative anymore. So we need to think about how to make these tools flexible enough that they can adapt to an evolving code base. We have a bunch of different applications, so it needs to be more flexible there. And then we're also, unsurprisingly, finding that those feedbacks when we couple to the atmosphere have a really big impact on our calibrated versions. And so what I'm kind of proposing for an idealized future, and this is still like a very much in the idea space right now, but where I'm hoping to go is that we train not just on one reanalysis product of offline simulations for the PPE. We introduce maybe that's where we run the bulk of our ensemble, but then we bring in some that are a small set of data that was run, a small PPE that was run in the coupled mode or from coupler history, and so that we're spanning like a wider breadth of the applications that this model is used in. And I think there's some really nice machine learning metrics or machine learning methods where you can train these emulators in this kind of multimodal data setting. Or maybe you just fine tune your emulator for a different ensemble that's case specific. If you want to run the model in F cases or coupled to the atmosphere, you have a small subset where you top up the emulator and fine tune it for that application. And then ideally, this is for the user community. I really would like this to be a system where the user comes with their parameters that they're interested in, and the spatial domain, temporal domain, and the metrics and observational data that they want, and they bring that to the system. And then our system returns either estimates of what CLM would give you, parameter sensitivity, or actual calibrated sets for that application. And so this is where I'm trying to head with this idea. I don't know if we can get there or not. I don't know how to bring in, what happens when we bring in new parameterizations into this scheme. But I do think that we need to head in this kind of more flexible, more adaptive methodology, because it's just not sustainable to have to run 2,500 ensemble PPE for every time a new parameterization comes in. And if we can't get to this, then we need much faster, computationally efficient calibration methods so that we can just deploy that on every case study. So there's kind of two paths I see going forward. Happy to talk about this more offline. And then lastly, I just wanted to take this time with the community to have a public service announcement that we now have these tools, FTorch, to bridge machine learning parameterizations and bring those into CLM. And we'll hear some more discussion of that from Aya, and there's, oh, slide got a little messed up, but there's a few different parameterizations that are in development right now. Aya will talk about the phonology parameterization. Oops. And there's a FIRE scheme, one for replacing pedotransfer functions, and then how to get parameters to vary spatially and temporally as well. So this is just to say that CLM has this capacity now, and so if you're thinking about developing machine learning parameterizations, please talk to us. A, develop in PyTorch, but B, come talk to us, and we're happy to help support that. That's all. Thanks.
Well, so this is kind of far out there in your vision, which I think is very cool. I've talked to a different group of people who've been working on emulators of the atmosphere model, right? And of course, that requires forcing files from the land to go into that. And I assume that in your vision of a CEMulator, that's great, would require forcing files from an atmosphere to go into that also as part of the parameterization. So what's the possibility that somewhere down the line you could have a CM emulator? It's hard to pronounce, even though it's cool.
We'll workshop
and,
that.
and a camulator, right? That could interact with each other rather than have forcing files. So you actually have some results of your land emulator going into the atmosphere emulator, and the atmosphere emulator going back into the land emulator. So you end up with kind of a pseudo-coupled model, a little bit better than what you had before. And is that so far out that you can't even envision it, or is that a possibility?
No, absolutely. We can absolutely do that. We're talking right now, so trying to capture the land atmosphere feedbacks.
Okay.
We want to couple to the camulator because it's a cheap proxy for a cam, and then we can try to capture some of the, and run, Fortran CLM coupled to the camulator. But there's no reason that we can't move towards CLM emulator coupled to camulator. I think that's very possible.
I mean, that'd be great, because then, it would open up a coupled modeling kind of approach to so many more people with so much, much reduced computational costs or anything. So that would be an outstanding future on this. Thanks.
Really interesting, Linnea. Just wanted to comment on, you said that the soil carbon looked like it was, there was a low bias and we weren't getting enough into the soil, so you might have to increase the residence times to bring it back in agreement. And I think that's a really good idea. I think that that would also help explain the radiocarbon measurements, and that for CLM5, it was picking up way too much radiocarbon because the soil turnover times were too fast. They were more like a decadal scale, and they should have been more like millennial scale. And so that would really help with the, I skipped the order of magnitude, but it's like, anyway, I think that seems like that would be the right way. So just cutting the flux in, but then expanding the residence time would help a lot with that too.
Okay. That's encouraging. Yeah, we're seeing like a lot of different lines of evidence that our biomass is just too high, our turnover needs to be faster and faster in the fast fluxes and slower in the residence pool. So it's great to hear. Yeah.
I'm sorry if I missed it, Linnea, or didn't digest it, but do you or how do you take into account uncertainty in the observations? Because like these flux towers, they have biases, they have errors.
Yeah.
Is that part of the scheme as well?
Yeah, so we're currently only using gridded global observational products. They're all on ILAM. And my estimate of the observational uncertainty is just the spread across products. which is an underestimate. The talks this morning talked about how much we're underestimating observational uncertainty, and I would love to bring in more robust estimates from observational uncertainty from people who know what they're doing. So very open to that.
Great. Thanks, Linnea. All right, our next speaker is Ignacio, who's going to talk about Plumber 2 simulations.
Great. So I'm Ignacio, and I'm going to present like how we also use simulators to Plumber 2 flag towers. So Gavin Nowitz led this Plumber 2 paper where he compared 20 models and 7 benchmarks. And there is the simplest benchmark with a linear regression of the fluxes using only shortwave radiation, and a complex benchmark with an LSTM model. The models use default parameters, there is no calibration, and we're evaluated using the entire period. And long story short, the model didn't do really well. Like all of the models were outperformed by a simple regression for sensible heat. The LSTM model outperformed all the models for latent heat, and there is no relationship between the level of complexity in the models and their performance. So GAV concluded that basically this raises the question of where the land surface models are too complex for the level of fidelity we're expecting, or the models are perfect, but we are unable to precisely prescribe each parameter for these simulations and global simulations. We're actively hindering this ability to get the right results. So basically, we have a problem with the parameters, the same in the same as Linnea mentioned. So this study addressed identify the key parameters that controls latent accessible heat and estimate optimal parameters. So for this, I use a different model. I use SUMA, which this model. It simulates the conservation of mass and energy, have multiple options. We have different solvers so that we can play with that, flexibility to test the models, and multiple options for like horizontal and vertical heterogeneity. So, and we first did sensitivity analysis with only the measure only fluxes. We divided that into calibration and validation. So the first 50% and the second 50%, we use KGE, which is like a nice metric. So we have a percent correlation part, an alpha, which is like a variability, and a B is a bias term, so difference between the means. And from the 170 stations on the Plumber, we only use 124, so we remove a station with less than 2 years and unreliable observed data. So we did sensitivity analysis, determining the mean and the maximum bounds of each parameter, 4,000 runs for all the sites. We ran the model, we evaluated the sensible latent heat, determined the first order sensitivity, and identified the key parameters. So this is like the key parameter for latent heat, and we can see there is some differences between like different phenologies and like how important they are, but there is some agreements in some parameters. So like basically turbulent parameters and soil parameters are the most important in line we're expecting. And for calibration, we also use emulators, but in another way. So there are two kinds of emulators, like the emulators that aim to reproduce the entire time series of fluxes directly, like bypassing the model, and emulators that try to reproduce the dynamics between parameters and objective functions. So in the model, in this case, the model, like in this case, SUMA represents the fluxes, and the emulators use it as a surrogate during calibration. And this is quite fast. Like usually every run of the model takes 45 minutes, and with the emulator, we do like 0.072 seconds, which is 37,000 faster. So there is quite an increase in that way. And for the calibration, we use the approach that Wokshan, Andrew Wood, and Sean Swanson developed. So we then define like a sample size and run the model. In this case, we ran 500 times the model. We train an emulator. We optimize the emulator using genetic algorithms. So we run 25,000 times the emulator with this set, and we get we run the model with these new parameters. And then if these are not good enough, we go back again, we retrain the emulator with new parameters, and we did it 6 times for every of the experiments. So there is like a lot of simulation, and we can see how the emulator was able to improve the models. So we did a single site emulator for like a single site. The emulator doesn't know information about other sites. And we did like a large sample emulator, which is a single file that has the information of all the models. And these, so it has the parameters for all the towers, the attributes for all the towers. So we have a few attributes like leaf area index, like the altitude of the tower, and we have a metric. And just to constrain the results, we actually calibrated using a normalized version of KGE, so we reduce the importance of the outliers. So first we can start with like a single site emulator in latent heat, and basically gives already good results. So we calibrated in the last part, so the upper part is latent heat and the lower part is sensible heat for all these plots. So, and there is a few references. So in blue is the summa default, like with no parameter optimization. Then we have the linear regression of the plumber, which is in red. And in black is the LSTM reference. So these are the references in the same period. So like during the 50% and the second 50%, but were not calibrated using the same strategy. So the LSTM was not calibrated using the exactly same configuration. But it's a reference. So like we can have an idea how we're moving forward. So basically, this simulator was able to outperform the LSTM and both benchmark for latent heat. Same story for sensible heat. So in sensible heat was more difficult, what is in line with the plumber to paper. So like we were able to overpass in the calibration period the LSTM benchmark, not in validation. And this is in line with the plumber to paper, where like they show problems trying to represent the sensible heat. Then we combine them, and in like an emulator that tries to get sensible heat and latent heat at the same time. And actually, it had very good results. So like it has comparable results as the single site emulator for like sensible and latent heat. So we didn't do much losing when we try to have two objectives at the same time. Then we move to a large sample emulator. So in this emulator, we try to have one single file, one single model for like a Python model for all the sites. And we basically try with 50 parameters and 30 parameters to see the importance of like how many parameters we're using. And basically both are able to outperform the LSTM. More parameters did give us a better results. So like the simulation with 50 parameters had a better performance. And we didn't see saturation, like when you start achieving the same performance with more parameters. We didn't, like, when we are trying to calibrate latent heat, we don't see as good results in sensible heat and vice versa when we have only one objective. For sensible heat, we did get better results in the, better than the single site, but we're still missing some stuff in the evaluation period with latent heat. But still the same, like with more parameters, give us better results. And then we did both, like, and this was our best result. So this outperforms, like, for latent heat outperforms both the calibration and validation, and for the sensible heat outperforms the training, and it's very close to what we observed when we focus only on sensible heat. So this experiment focused on both. Then we try to make experiments like original experiments. So basically, we take 20% of the towers and we train the emulator on the remaining 80%, and we test the emulator in the 20% that we are not training. So the emulator is trying to see how it will work in this 20% that's not being fed in the emulator. And we take 20% of the towers out, and we have actually very good results. So there is two ways to evaluate this. We can evaluate the post facto, so the value that actually the model has, or the value that the emulator has. So the emulators and the model disagree a bit, because the emulator is actually a bit more optimistic, so they try to get better values than the model is actually getting. But both values, so the line, like, the first and the second line, like gray and blue, are trying to give us good relation, show us that the emulator, even without the towers trying to be simulated, it has like a good performance. So as a summary, so letting a sensible heat can be calibrated and outperforms the benchmark. So here's a calibration with all the elements. So for the first part is latent heat, and we can see that the large sample emulators outperform the single site, which we're expecting. And when we try to calibrate for both, we actually are not losing performance. So we are in the same range. We have not the same, but overall we have the best performance overall with the emulator that tries to do both. We are able to, the LSE performs more parameters that give better results. The method do provide good results for regionalization, so the emulator is able to find parameters in sites that it has never seen. And there is limitations in capturing sensible heat. And this was in very line with the first figure that I showed, that there is problems any model was able to replicate sensible heat in the Plumber 2. So we are in the same line. We have better performance because the model is calibrated, but still there is problems representing sensible heat in models. But we do know that this model is really cheap, so we can run this only using 1,000 simulations of the model, so it's quite cheap, and we can get very good results. And we can have both fluxes good at the same time. So we are trying to evaluate the impacts of the different decisions, like how we can improve a bit more, understand what decision is going on. Try to now replicate the opposite way, so we can try in the 20% and replicate the 80%, which already know we already know, seeing early result that is actually doing what we expect, so a reasonable result, and thinking how we can improve or sensible good results, sensible heat. So during this remaining of the year, we try to apply this same approach to CLM. So an acknowledgement to all the people that supported us, and thank you.
Thanks, Ignacio. You mentioned that the emulators are generalizing to other sites that they haven't seen before. Mm-hmm. Was that true for all different plant functional types? Is it true for grasses, shrubs, or only the sites where we have a lot of different sites for broadleaf evergreen trees or something like that?
No, it was true for all sites. So its cross-validation group is completely random, so it has a bit of everything. And there are sites in the Plumber 2 where there is only 5 sites, for some PFT. So the amount of the sites are not equally distributed in the Plumber 2. So even in their site that the woody shrubland, there is 5, it still got good results. And the results are measured against the benchmark. It's better than the benchmark or not. So for some sites, the benchmark is not really high. It's not really high. So but it's easy for the model to surpass it. And for other sites, especially for a forest, the benchmark is quite high. So the model has to more. We need a more robust model to actually surpass the benchmark.
Other questions? I guess this is maybe a question for both of you guys. Just so thinking about these single point calibrations, any of us that have done single point calibrations, so it's almost you look at the model and the results are terrible out of the box, and so you throw out a bunch of parameters and then you either hand tune or try to calibrate. And I'm curious if there's ways, and with all the PFT specific parameters that we have and the variation in plant, in those parameters, you might not expect that a generic C3 grass would be well captured at your grassland site or whatever. So I guess I'm curious to what can we learn from these, whether it's Plumber 2 or Neon or other supported tower sites in our calibration that could actually be applied globally? Is it just the global parameters that we try to fix? Or what's the handoff between site level calibration and global optimization methods?
I think one of the keys that we can run these models way faster. So we can test different strategies of calibration faster. We can try if we tune this, what happened? And we can, instead of waiting long hours, we can have even a result of any model in a few hours, way faster that we'll have. So we can have a good results of many sites representative, and we don't lead in the same way with the observational uncertainty, because we have this is more constrained uncertainty with observations.
you want to add anything?
I think we do just have a really big gap between the top-down calibration methods and the bottom-up methods, and we haven't figured out a nice way to bridge those. I can envision handing off posteriors on the parameters from the global calibration to the site folks, and hopefully that narrows in your search space a little bit, but I think we can do better to help those two methods meet in the middle somewhere.
You gotta hold it, sorry, Andy. You gotta hold it, sorry. Aya, are you around? Oh, she's online. Do you see Aya online? No, uh-oh. Yeah, maybe while we're looking for Aya, who's our next speaker, we can hear from Andy.
I just wanted to say nice presentation and also concur with your assessment that these emulator-based approaches are such a nice, like fast, efficient tool for testing ideas. One of the things we had thought was that in some models we have more of a hierarchy of like global to local scope of parameters. And we can evaluate using these emulators and distributing parameters either globally, like as constants, or completely locally fully distributed, or semi-distributed as parts of parameter libraries for like a crop type or something. We can evaluate using different alternatives to figure out which of those really do need to be fully distributed versus can perform just fine in a library or even can just be left at a global setting. So I agree with that. And then I was also going to say, like relative to Linea's comment, we're just submitting a paper this week that kind of illustrates how you can use these emulators to generate sort of ensembles of performative parameter sets for the entire globe. Then you can go back in later. So those are like pre-trained like priors, and then you can go in and select them. If you have any other local information that you can bring in of different types, even multivariate, you know, even statistics, not time series, you can use those to preferentially select the best pre-trained performative parameter set. So there's just a whole range and family of techniques that can be brought to bear on this now that we're starting to work out how to use the emulators. Thanks.
No, definitely. Like there is a lot of decision that you can apply in this, and like we can try to play. There is a lot of flexibility with this approach. Like the approach is very simple, so that's why simply we can do flexibility and like keep some parameters fixed. We have experience with like for clusters, so we have like in the same that very similar. We have a cluster with for every PFP, but we have when every site is completely they move all together and they move like faster. So like we can do a lot of experiments and like figure out the best way to calibrate all the sites.
Great, thanks. We might call in Audible because I don't know where Aya is, and we're going to try to track her down. But Flavio, do you think you could save us? So this would be a good transition to start thinking about hydrology a little bit.
Wow, interesting. Cool. Well, thanks for having me. I'm going to present work that is really Hanjun Kim's work, a postdoc that has been working with us on this project, who's not here, I think mainly because he's interviewing for his next job, so fingers crossed. Yeah, so this is some work together with people here at NCAR and in the room. It's kind of a joint project between some NOAA funding and then also eventually some DOE funding, trying to look at runoff sensitivity, expanding on some earlier work. This is part of sort of a series of things we've done in my group, and just want to shout out for some work that Yaning is going to present tomorrow, a grad student, I think tomorrow or Wednesday on tidal connections, but we've kind of like had a series of papers on kind of like what drives drought over the southwestern US, and like in the process of that, you obviously kind of like go between teleconnections all the way to hydrology. But I'm not a hydrologist by training, despite the best efforts from Andy Wood when I did a postdoc with him. But yeah, I like to dabble, or we like to dabble. But yeah, today we're going to talk a little bit about runoff sensitivity. This goes back to a paper actually that we published during my time here at NCAR. That was just like a case study on 3 basins where we looked at runoff sensitivity and whether it is right or wrong in climate models, and what that could tell us about future runoff changes coming out of GCMs, and also maybe how we can improve models. So just sort of a quick, maybe this audience is pretty familiar with this concept, but fundamentally when we think about runoff sensitivity, it's sort of a simplified description of what happens with rain once it falls onto the land surface. So it's basically a simple regression model between changes. This could be on inter-annul basis, but also, as we'll see, on climate change basis. Changes in runoff or stream flow expressed as changes in precipitation, and changes in temperature, temperature being kind of like a proxy here for evaporation. So a very simple model of describing changes in runoff. And the idea is that, yeah, this would encompass all the complicated things, obviously not perfectly by any means, that affect the translation of precipitation to stream flow. What we showed in that paper is that you can estimate these runoff sensitivities based on inter-annul variability of stream flow, as well as precipitation temperature from observations within some uncertainty, sizable uncertainty also coming from internal variability. We have a limited observational record that we can use. So here's an example for the Upper Colorado River Basin, where on the x-axis we have this the precipitation part of this sensitivity package. So we have precipitation sensitivity, so how much is runoff changing in response to changes in precipitation, and then on the y-axis, how much is runoff changing in response to changes in temperature. And so then these 2 red bars are observational estimates, and then all the blue circles with uncertainty around them are, I think at the time, CMIP5 models. And so the point here is really that this metric can be calculated from observations. So I'll try to make the point why this is valuable, but also that climate models are kind of all over the place. Some are closer to what we think reality is doing, and others are a little further away. So there are potentially biases in this sensitivity metric. Why would we care about the sensitivity metric if we think about climate change? It turns out that these sensitivities are, like, surprisingly maybe predictive of future behavior within a model as well. So what's shown here is on the x-axis, again, for the Upper Colorado Basin, for a 2-degree warmer world, the changes in runoff as they come out of CMIP5 models. And then on the y-axis is basically a prediction using future changes in precipitation and temperature, and historically, each model's historical runoff sensitivity. So these parameters, sorry if I go back briefly, this alpha and beta in this kind of regression model. And so the relationship is relatively good, meaning that this sensitivity metric based on inter-annul variability in the historical period it still acts in the future, and it acts on these longer timescales. Not perfectly, there's other things that are changing, obviously. But so yeah, roughly predictive of future behavior. And so obviously this is kind of an opportunity to use something we can observe to constrain future projections on stuff that we can't observe. So like at the time in this paper, we just looked at 3 basins in the Western US. And then as part of this project, now Hanjun has on the one hand expanded this globally and to see if it works in other basins, but also done a much better job than we did at the time in kind of testing the robustness of this idea. So what you see here on the top is now CMIP6 simulated changes for runoff for different basins around the world for a sort of a middle of the road scenario there. And then at the bottom is these same changes predicted again using this model simulated changes in precipitation and temperature in each basin and the historical sensitivity from each climate model. Again, so this kind of assumes, can I predict future changes in runoff, assuming the same relationship between temperature, precipitation, and runoff that has existed over the historical time period. And again, for a lot of basins, it turns out that this works. It doesn't work everywhere. I mean, wouldn't expect it to work everywhere. There's so many things that change in the future plans, snow goes away, precipitation phase, etc. So it's still interesting and useful to know that this works in some basins. So then we can like sort of start to say like, well, okay, the sensitivity is potentially useful to constrain future projections. Like, okay, how good are the models at like actually simulating the sensitivity of the historical period? This is again sort of expanding on this using, I can't call this observations, but reanalysis of runoff, precipitation and temperature to assess, or just to like look at the precipitation sensitivity and the temperature sensitivity in reality in quotes. So that's what these maps look like. So you have like largely positive values, of course, for precipitation sensitivity. So yeah, if it rains more, there's more runoff typically, and negative values for temperature sensitivity. Now we can look at how basically this looks in CMIP6 models. So this is not the differences, just the actual values coming out of the models. And so we see generally CMIP5 is overestimating this precipitation sensitivity. So runoff reacts too sensitively to changes in precipitation, while it tends to underestimate, but not everywhere, the temperature sensitivity. So reality sees, for example, steeper declines in runoff in response to warming than the models predict. Now to kind of illustrate how large this effect is and where we might actually benefit from better constraining and better modeling runoff sensitivity, we can play this game where we say like, okay, we know model sensitivities are biased, we just plug in the observed ones. We can maybe justify doing that because I earlier showed that the historical observable runoff sensitivities carry some value, some predictive value of the future behavior. So we take this same kind of equation, we just plug in the observed sensitivities instead of the modeled ones, and we see how this like affects both the direction but also the spread of future projections. So like just developing an emergent constraint or an observational constraint on these projections. This is where Hanjun did a lot of work of like developing a couple of checks on this, which largely like greatly reduces the number of basins around the world that this actually works, just sort of as a caveat. So this first step is what I already told you. Can we use historical sensitivity to predict future changes? It doesn't work everywhere. You can like kind of track these numbers. It works in 170 out of 131 of these large basins around the world. Then once we apply this observation constraint, is the constraint change in runoff actually different from the simulated one within internal variability uncertainties? It's not in a lot of basins, so the constraint doesn't do anything. That further reduces the basins. And then this is an important one and kind of like sort of the tough nut to crack. Of course, there are places where the sensitivities themselves would change, and climate models would tell you that, right? Like if there's changes in vegetation, et cetera, that would change that. We can only really justify applying this constraint in basins where this bias in the sensitivity in the historical period is larger than any change in sensitivity that the models predict. So we're taking the models at face value. If they say there's a big nonlinearity, runoff suddenly behaves very different in the future, and that has a bigger effect than the actual bias in the historical period, then we're like sort of, okay, we can't do that for this basin. And then ultimately we do a check whether this constraint actually works in both CMIP 5 and 6. Once you do that, you're down to kind of 41 basins out of 131 where this constraint works, where you could sort of justify, I can like tell you a sort of a more constrained answer to the question of how runoff is changing in a warming climate. To kind of like show you how the pattern of that looks like, on the left we have just the actual predicted changes in runoff again for the same time period emission scenario in CMIP 6, and then on the right-hand side is after applying these constraints. And again, there's like, it's a bit hard to see, but fundamentally only the basins that are sort of solidly encompassed are the ones where this actually works, those 41 basins. But the upshot really of this whole thing is that for many of the basins, especially if you look at the ones where we can do robust constraints, we tend to get lower runoff in the future. Or like if there's a positive prediction originally or projection, then that's weakened. If there's a negative one, it tends to get more negative. So generally, that's kind of the effect we see. Most of this comes actually from the biases in the temperature sensitivity. So really the story that according to the sensitivity metric, models are not sensitive enough to temperature changes, and so they don't lose quite as much water in the models as they should if we trust observations. Now the hard part is to kind of like figure out why. While we were working on this, there was another paper that tried to do the same thing in a similar way. Actually, I think it was 2024. But yeah, very much came to the same conclusions in that sense, yeah. So future streamflow declines might be less if you trust this kind of method. I forgot to take my time, but if we have a few more minutes, then I'll show you how far or not far we are with kind of trying to figure out where these biases actually might come from. So what's shown here is a correlation across all of these basins between, in this case, the precipitation sensitivity and different mean state or other metrics that you can get out of the model. So the first question is obviously, well, for example, is precipitation sensitivity too high or too low in models that have or too wet or too dry or too warm and so forth? And so the main thing here is that for a lot of these mean state metrics, temperature, precipitation, runoff itself, ET, soil moisture, etc., there's not like a universal or global correlation between the precipitation sensitivity and the mean state, which means mean state biases aren't like always going to help you explain why the model is wrong. You can kind of point out a few maybe sort of even intuitive biases. So you have this, for example, this relationship with ET. So like if you have a model that has higher ET in the mean state, in a lot of bases, that also results in a higher precipitation sensitivity. So if you then have a model that has too high of a precipitation sensitivity, you can like maybe start by figuring out why you have too much ET. Of course, it's sometimes a little circular in a coupled model, but that's kind of the search we've done so far. Unfortunately, for temperature sensitivity, there's nothing that kind of stands out, again, across these 131 basins. In some basins, some of these correlations are significant, but there's no global culprit for why models might or might not get these two sensitivities right or not, which probably doesn't come as a surprise for most of the people in this room, especially after the last two talks. We can look at the spatial patterns of this correlation that kind of should point us to what potential mean state biases or other metrics are at the root cause of these sensitivities. And again, it's a pretty heterogeneous pattern. Sometimes these correlations aren't significant, so it's kind of hard to know where they point. There's maybe something in some, and I feel like we should also look for some regional coherent patterns, right, in the hope that there's at least within one region where you could argue that the hydrology is somewhat similar, that there's something systematic wrong that makes these sensitivities be too high or too low. And so this is an example where there might be something there where mean evaporation and temperature sensitivity are correlated. And it's also a region where, I don't think I've shown that earlier or not highlighted, where we do have sensitivity biases, right? So ET biases in this region would, like fixing those would lead to better representation of these sensitivities. But of course, this is kind of the start of a search in the needle in the haystack. And so some next steps, just to facilitate other people working on this, because Hanjun in particular, and this project is kind of sort of coming to an end. He's implemented this in the NOAA MDTF package, which is part of this project, and we're also working at getting this into ILAM. And then, yeah, people here, Summer, Sean, and Andy, I think as part of some other projects are looking to look a little bit at smaller scales. We realized that if you have a runoff sensitivity bias for the Amazon basin, what does that mean, right? Or some of the basins that span a lot of elevation gradients. And so I think the way forward is to look a little bit, yeah, more regionally refined in terms of figuring out what might be wrong. And I think all of this work will probably focus just on the NCAR model. Don't think we'll be able to answer all the model bias questions of all the CMIP models. And the PPEs, we haven't really worked with them too much, but they obviously offer another opportunity to see which parameter variations improve runoff sensitivity. Because the nice thing I didn't mention at the beginning, this is a sensitivity that, as far as I'm concerned or I understand, isn't really talked about in model development. So it's like something that emerges from all the work that people like you do in developing these models. So it's an independent metric that we can maybe keep track of. I realize I put in a slide at the very late moment, but I think I didn't update. That. Yeah, no. So we'll end there. Thank you.
A question and then maybe another question. when you were showing your sort of validation, you're correlating against different variables, was that all from reanalyses on the left there? Or the source of those terms, ET and Q? And
no, this is actually, yeah, I realized that this figure is too, I should do a better job of walking through it. This is just within the models, right? Where is there a relationship between the mean state, just the mean state,
within a model, okay,
and the sensitivity in the model as a starting point, right?
Right.
Of course, yes. I think where you're getting at is that, like, let's say you can identify that, and then you go and say, like, okay, our model's too warm or too wet. Once you get to variables like transpiration or other things, what is your reality that you can benchmark again?
Yeah, because when you start looking like in a Boudico framework, runoff sensitivity is ET sensitivity, right, on a kind of a larger scale. But then you start tying into vegetation, the carbon cycle. There's a lot of things that in reality are also affecting ET that maybe or maybe not are occurring in the models. So, I mean, you know, just trying to diagnose the processes when you say what are the root causes, I mean, it may be way out there.
I mean, and this is exactly, again, the right room to give feedback on what is the most effective way to make progress on this. Yeah, thank you.
I was wondering about your second criteria for whether this is useful, and it was whether they're different. Was that with the model ensemble mean? Because it seems like it still could be useful to reduce the uncertainty even if the mean is the same.
Yeah, I think we have, if I remember correctly, there's two tests wrapped into this. Yeah, one is on the mean and also the spread of the uncertainty around it. Because you could have a case where, like, let's say the multi-model mean doesn't budge, but the uncertainty gets smaller, and that's worth reporting. It turns out, actually, generally, maybe not for every basin, that's not the case, because once we, and this actually revises also some of the results we had in our 2019 paper, once you do like a thorough accounting of the observational uncertainty that is wrapped into the fact that we only have, let's say, 60, 70 years of data that we can maybe even use from observations, if you sample that from a large ensemble, the uncertainties actually sometimes become larger because the observation record is still a bit too short for all of these basins to estimate runoff sensitivity very robustly, even in reality. Yeah, so we find actually that we are not often able to reduce the spread even of the CMIP projections by doing this. Yeah.
Other questions?
Hi, just one study I look at like the uncertainty in precipitation data products, and then for European catchments, and I noticed that was like the uncertainty in precipitation data propagated into models, especially for runoff, but also for evapotranspiration. But when I was comparing with some reference data like GLEAM, I couldn't see that much sensitivity that we have. So I was curious if you have looked at any. You mentioned also you haven't looked at like any like reference data for evapotranspiration. You have any idea for like which would be possible if we can check the validity of the evapotranspiration data for that?
Yeah, so this, for the revisions of this paper, which are ongoing, Hanjun has been starting to look at GLEAM, among other things. What we did do so far is like sample different observational precipitation and temperature products and runoff products, which is, yeah, there's no global graded runoff data set really observed, but sample those to create an ensemble of observed runoff sensitivities. So there's a fair bit of uncertainty there already, and then you probably want to do the same for any test against or with other metrics like ET or so forth. Yeah, that's kind of ongoing. Okay, thanks.
Great. Thanks, Flavio. I think Aya's never came on. Is that accurate? Bombers. Okay. So then is Wan Young online? Yeah? Do you want to share your screen?
Oh, hi. Should I start sharing?
Yeah, can you share your screen? And maybe while you're pulling that up, do you mind telling us what time it is in Korea?
It's it's 7:30 in the morning, so it's not bad.
Well, good morning. Thanks for joining us. Great, we can see your screen.
Um, okay, good. It's afternoon, right? It's good afternoon, everyone. I'm Hyun from Yonsei University, South Korea, and I'm currently now a PhD candidate. So I will be presenting on my ongoing work on enhanced wetland representation and parameter optimization for carbon flux simulations and CLM5 fates. So the ecosystem I'm particularly interested in is wetlands, which are known as significant carbon reservoirs, but simultaneously represent the largest natural source of methane. And as far as I understand, there are some further development required for the current process-based models, like conceptual understanding and its technical incorporation, and especially addressing like parameter uncertainty. And additionally, since CLM 4.5, the wetland land unit is no longer active, but is now treated as like an inundated fraction in the grid cell. So for like point scale simulations, I'm interested in at like the specific wetland sites. Wetland specific environments must be established. So I'm working on establishing wetland-specific modeling environments in CLM5 fates that can incorporate site-specific vegetation and soil characteristics and identify key parameters governing carbon fluxes and optimize them using observational data, especially for the freshwater wetland in Korea. So here is a brief introduction to our studies. So this is an artificial wetland located in South Korea, and its mean annual temperature ranges from -15 to approximately 30 degrees Celsius, with mean annual precipitation of about 1,400 millimeters. And the dominant vegetation consists of common reed and bulrush, so they can be classified as PFT C3 grass. And we established a new flux tower 2 years ago and have been collecting data along with monthly chamber measurements of CO2 and methane since last year. So first of all, to define key parameters for optimization and carbon flux simulations, I previously conducted sensitivity analysis on permanent freshwater wetland sites with similar vegetation using FluxNet methane database, so some sites in California and Ohio. And I calculated the polynomial chaos expansion-based Sobel indices and used this total Sobel index to also account for interactions among parameters in determining key parameters. And after I define like the key parameter set, I applied like this generalized likelihood approach to derive optimal confidence intervals for each parameter using RMSE as an informal likelihood function. So here on the left is the example of Sobel indices calculation for all like 49 parameters I examine. So I calculated the index for these 4 fluxes, so NEP, GPP, and ecosystem respiration and methane flux. And then I selected the top parameters with the magnitude of the Sobel indices. And then using this parameter set, I applied like the glue confidence intervals, like I mentioned before, with Latin hypercube sampling. And then so that I can obtain like this overall parameter density distribution for each of the site like this. So this is the figure of like all of the key parameters and its combined parameter distribution with all of these sites so that I can get like the general information of like which intervals I should use for like the optimization for my site. And this is how I established the wetland modeling environment within the CLM. So first I started by reactivating the wetland land unit with hydric soil and vegetation growth, similar to like the current vegetated land unit. And currently I have set the soil in constant saturation to simulate like the permanent wetland. But since we are collecting like soil moisture and water table depth data, I plan to incorporate these values in later soil hydrology settings. And we also modified the century decomposition pool and carbon transfer pathways using the microbial carbon use efficiency concept introduced in Tao et al.'s paper in 2023. So if you look at the figure like below, this this scheme essentially redefines the soil pool types with explicit inclusion of microbial carbon pools, like such as dissolved organic carbon and microbial biomass and enzymes and mineral associated SOC, along with defining carbon transfer fractions using like this carbon use efficiency concept. So this modification actually introduced new soil respiration parameters to the model, and this like carbon use efficiency values is something that we can obtain from the laboratory experiments. So we are now collaborating with other lab to obtain this value and implement it in the model. So for now, just leaving this new parameter as like a parameter we need to optimize along with the previously defined key parameters. I applied the optimizing scheme using the BOA wrapper. So this is something that the Professor Gilbore's lab in Ohio University developed. So his team developed this wrapper for ELM that can optimize parameters simultaneously during model runs. So I incorporated this into the CLM. And according to his team, this methane module parameters do not affect like GPP and ecosystem respiration, especially for grass PFTs. So this makes like this hierarchical optimization scheme logical, which optimize the GPP related parameters first, and then move on to respiration, and finally the methane. So this is the, like my result. So we evaluated the optimized daily flux against the default like parameter run, and you can see error reductions were achieved across all of the carbon fluxes compared to the baseline simulation, having like this methane flux RMSE reduce the most by 94.5% decrease. And this is the like temporal plot of the methane flux. So the top one was with the default parameter and the bottom one with the optimized parameter. There are some like overestimation during the summer, but we are now thinking this is because that I have set the soil into constant saturation, so there is some like overestimation happening in that season. And we also compare like the model's hourly diurnal pattern, and we focus on like the peak growth season in July and the Cenacine periods during October. So results also showed that there's an increased uncertainty in October compared to July's diurnal cycle. So this indicates there are greater uncertainty to be treated during winter and non-growing seasons. And since we are also doing like the monthly chamber measurements for this carbon fluxes, we compare like the monthly model results with the chamber measurements. Though they were within the similar like ranges, we need to address like the temporal scale differences because this chamber measurements were conducted only once a month and during peak daytime hours, like between 10 a.m. to 2 p.m. And lastly, the other component we have begun working on is like the methane module improvement using observed Aeronchema conductivity of wetland vegetation, also in collaboration with The Ohio State University. So in vegetated wetlands, vegetation methane flux through Aeronchema is one of the major transport pathways, but current model equations contain parameters that are like difficult to measure directly and are highly uncertain. So we plan to replace these equations with observation-based Aeronchema conductivity and LAI, which we could gain from like leaf chamber measurements along with pore water concentrations. So Professor Gill's team have already tested this method at one of the wetland in Louisiana. So we are trying to expand this approach to CLM and to Korean wetlands. So yeah, this is all. Thank you.
Great. Do we have any questions?
Thanks for your interesting talk. I'm wondering if you looked at soil carbon at all in your optimized model, given the changes you made?
Oh, yes. I don't have a figure here, but I could see that there are more carbon accumulating compared to the one that I used, like the default soil parameters. But I didn't make like the direct comparison with the site data about the soil carbon.
Great, great. Thanks. And we found Aya. She's here. Do you mind pulling up Aya's talk? Cool. Go ahead.
Great, thank you. Sorry I scared a bunch of you. I've never been to this spot of NCAR, but I'm happy to be here and I'm happy to be back in Colorado, and I'm happy to be talking about some of our work and some of the work that I've been collaborating with Linnea, Dave Lawrence, Adriana Foster, and my professor Pierre Gentine over the past few months, but over really the past few years at least when discussing it. And I'm very excited to be introducing it and getting to work on it more and more. So my project is about a phenology model to the CLM. And just to, I won't bore you too long with the motivation behind it, but I really liked this project ever since I started my PhD, just because of the ton of impacts that phenology really has and touches, from carbon, water, energy fluxes, wildfire risk, etc. So the motivation behind the integration with the CLM was a project that I worked on for a couple of years, which was to use a machine learning model called the temporal fusion transformers in order to improve phenology forecasting and modeling, specifically targeting seasonal variations and interannual anomalies, especially when it comes to different biomes and the tropics and grasslands as well. So this is just a little bit of a background from the project that came before this. My predictors were Era 5, Climate 4, period, as well as like static covariates such as soil texture, and then further filtered by the plant functional type that we're trying to model. And to introduce a little bit of background about this transformer specifically is its ability to actually understand what the model is learning and which time steps are most important due to the interpretable multi-head attention mechanism, and also to the variable selection gates that it has. So we can in turn have a good idea of which time steps in the past or in the previous seasons were most important, specifically drawing our attention to specific extreme events, for example, or also within those time steps, what was the future importance exactly. I used to train this model with solar-induced fluorescence, but we will be using LAI from now on later in this presentation. These are some of the primary results of that project, and you see how the temporal fusion transformer is able to get to very good results across different biomes, even in evergreen forests and grasslands, which a lot of models, and especially process-based models, fail to represent. This performance is also important to note that it is doing great in interannual anomalies. So it is able to predict an earlier spring onset or a later senescence based on the differences or possible like extreme weather events that happen and could change a specific site's phenology a specific year. And on the right, we have some results from the interpretable mechanism. So we're able to kind of untie and see a little bit of what the model is learning, specifically in what are the different impacts of radiation, water availability, or temperature, which one is most important and where in across different biomes. And I think it's interesting, you get to see very interesting gradients, especially across Africa, on where radiation becomes to be a more important factor on the start of the season or at the end of it. So I hope this was motivation enough to maybe look at introducing like a machine learning model for this specific task of phenology. And I wanted to give just a little bit of background of the phenology representation in the CLM or in other CMIP 5 models. Specifically, there have been a lot of studies that have done a little bit of a review of some of the most used models for phenology. And they consistently show an underrepresentation of the interannual variation, specifically when it comes to spring leaf phenology, and also a poor representation in terms of inner site variability when it comes to autumn leaf phenology. Across all models with both of those papers, the best models still had a 7 to 9 day prediction error. And this has cascading effects on the carbon pools that are then added or taken out. But on the right-hand side, you can also see specifically some of the bias that the CLM5 has in the seasonal GPP and how it compares to the FluxCom observations. Specifically, we see an earlier spring and a later a later fall compared to the observations in FluxCom. And so I wanted to look a little bit more about why that is and how CLM really gets to present or get to their onset and offset. And essentially, I won't bore you too much with the pseudocode that I have here, but spring onset is essentially all based on empirical thresholds, often extrapolated from temperate zones, specifically for the soil temperatures and for GGD, a critical threshold that is actually also a function of a mean annual temperature in that region and kind of acts as a surrogate of the chill-in requirement that some of these biomes have. And then in the fall, we really rely heavily on photoperiod as a trigger. As soon as a photoperiod is below 10.9 hours, then the offset is starts. Also, in both of these cases, the length of the onset and the length of the senescence is set. Onset is 30 days and senescence is 15 days. So no matter what can happen with the forcing data, we don't have any sort of control on the seasonal length or the length of the growing season that year. So this just motivates how much we do need like an adaptive phenology model and a model that can that tracks the environmental forcings rather than being so like set in stone. And I wanted to just address the question of why not like just a better parametrization and why trying to find a better parametrization can lead to some shifts in phenology. We really rarely can see an improvement on year-to-year responsiveness or climate adaptation in the long term of phenology, specifically when it comes to different sensitivities that plants get to develop over the years with the changing climate. And now more onto the results, and I hope that this just introduced even more like the importance of a long-term multivariate climate phenology effect. So we're using FTorch as an interface for Fortran to add this machine learning model that's based in PyTorch and add it to the CLM and be able to test it there. And then the first proposed method, or our first phase of this method, was to use the transformers trained weights as a way to get a LAI forecast of 10 days, and from there infer improved onset, maturation, senescence, and dormancy dates And the way we do that is we had to adapt a little bit our training pipeline to shorter inputs, so 60-day inputs of climate forcings, and getting us a 10-day forecast of LAI. And from that 10-day forecast, we use a method called adaptive local iterative logistic fitting method, which is basically a much fancier elbow detection method, if you want, that just says, here is spring and I'm very sure of it. And so that was phase one. We wanted to first have a similar or the same evaluation data set for the CLM and for this new method that we're trying to introduce. And so we used, the Morgan Monroe State Forest FluxCom site. And you can see here there's just another graphic to show the early onset that CLM does show for the USMMS site, also late senescence, so it is a consistent bias year to year. So these are some of the preliminary results after fine-tuning a pre-trained model on broadleaf deciduous trees in temperate zones, and then fine-tuning it on data from around the same region. We have predictions that are able to get quite accurately the predictions or like the observations of the FluxCom data with the R-squared of 96 overall. And then for the seasonal variations and then the anomalies, it is doing pretty well. But in the anomalies, you see like a drop in the R-square, which I think can be explained in just also the noisiness nature of the FluxCom data. And yeah. From there, I also try to get the onset, maturation, senescence, and dormancy dates from the CLM phenology module. And you can see here just how much the CLM is carries like a much higher bias than the temporal fusion transformers when predicting the onset, maturation, senescence, and dormancy. I don't have this up here, but in terms of days or prediction, days of prediction error or bias, the TFT has less than 2 days over all phases of phenology, whereas in CLM, in some cases, it got up to over 30 days of prediction errors. And yeah, here are just some more figures. The R-squared for the CLM is negative, but we're hoping to just like have like a better understanding also of like this performance and this bias like across like more biomes than just one. Next, I wanted to just talk about some more plans and more ideas that we have discussed about this project. The second one being having a more dynamic carbon allometry method, essentially to be able to have a realistic climate sensitive and seasonal LAI profiles. So be able to show the diversity in like the different slopes of the onset and leaf out, and also senescence across different plant functional types and different climates. Now we have set allocation parameters between that go between the different parts of the land. The soil, the leaves, or the roots, etc., that do not change like throughout the season. And so within 30 days in the onset and within 15 days in the onset, we have a linearly growing function that allocates the carbon consistently every year the same way. So we want to have like more realism in how LAI is presented and how LAI is derived. Next phase was to also think about ways to have the different parts of the phenology module now in the CSM be more integrated, specifically in thinking of changing land covers and updated land covers. We don't want to perhaps only have certain pixels always go to stress deciduous phenology subroutines or evergreen phenology, but perhaps think of a more data-driven and holistic phenology method. Yeah. And these are just some key takeaways. Phenology is a key uncertainty in land modeling. It affects carbon, water, and energy cycles, and even just some days of prediction error can lead to cascading effects when it comes to carbon pools. And now that we are able to have real-time machine learning inference in the CESM via FTorch integration, I'm very excited for all the doors that it might be able to open and finally be able to replace some of these hard-coded rules that we've had and in adapting phenology to be more climate sensitive. And with that, I'll take any questions. Thank you.
Questions for Aya?
Oh, thanks, great talk. I just want to think if have you looked at like any specific year, like 2012 was earlier phenology, and because of that also we have, I mean, not because of that, at the same time we have also drought at that year, or heat waves that we have also earlier phenology in Europe. Have you, I think, like machine learning can produce like a specific year phenology? Have you looked at that?
Yeah. Thank you for the question. That's a great question. I don't remember looking at 2003 or 2012 specifically, but I looked into a lot of specific years and maybe like very specific regions as well, and try to have like more of that understanding of what climate variables are playing a bigger role and when in the year. I think like if we go back to like my earlier slides, this one right here, I don't remember where this one exactly was from. I want to say that it was from Western Europe, and that it probably was over like a few years at least. I want to say from 2017 to 2021, but you're able to see the relationship between specific maybe precipitation events in like the past year's spring and the relationship that it has on like this year's spring. And yeah, I think that is very interesting and exciting to like maybe look at it more and maybe answering a specific phenology question or climate question.
Great. One more question from Jim.
It's a really interesting talk, really nice work. I guess in some ecosystems it looks like the senescence and the early onset are connected in that if you, building on the other question, you know, if you have an earlier onset from you might be burning through your water or your nutrients more effectively, and so then you can see a shutdown in the middle of the season or at the end of the season earlier, like in the Canadian wildfires in 2023 and 2024. There was a really early spring and GPP was higher and the transpiration was higher, and so it kind of, you can see a negative GPP anomaly at the end of the season. So if you, I guess my question is, have you thought about, is there a way to like have some variables that have kind of a ecological memory that connect the onset to the senescence?
Yeah, I think that's a great question. And that's like the motivation behind a lot of this work was to have like long-term like dependencies and connect specifically the onset to the senescence. In my first project, I did use a context or historical context of 365 days. So for predicting the senescence, it was able to draw upon whatever climate variables were happening or the trends of the solar-induced fluorescence in during the onset. And you would see also, so this is just one example where we're predicting the onset, but in other examples where we're predicting the senescence, you would see much stronger bands, and so attention scores that are related to specifically the spring of that year. So yeah, that's definitely something that I've seen.
Great. Let's thank Aya and all the rest of the speakers one more time. And I think there's a poster session and reception out now, so if you want to grab anyone and ask your burning questions, that's a great time to do it. Thanks.